Welcome to this training. This is a total of about 5 hours of video, of which only first 30 minutes is for the owners and business owners in process industry, and the first hour and 15 minutes is actually for the general management who are making decisions towards having these digital systems and ensuring their benefits to the company. And the first 30 minutes for the owners is really the strategic discussion of how digital fits into their business strategy. And the rest of the video is about utilizing all these techniques which we hear often, data analytics, AI, decision making, continuous improvement using the data analytic approach. Uh, welcome to this training again. My name is Samir Gizre and I will be your instructor for this training. So let's get started. Now, in the first session, which is for the owners of businesses and companies who are running process industry based businesses and the general management of the company. So in this short session, we will talk straight about, is digital worth taking seriously, and if so, how seriously? Or, is digital firmly in place of company strategy like other functions of sales, manufacturing, etc.? Then we will see how the plethora of the digital systems, hundreds of those which we hear from various vendors, consultants, etc., how they can be classified as infrastructure and decision making systems, and then how this classification can be leveraged to take decisions and implement various programs very effectively. And uh, going forward, we will also talk about very briefly the digital strategy and roadmap of companies in process industry. Uh, so when we are looking from the point of view of owners of a company running process industry business, who are not necessarily heavily into the technical aspects of processes and systems of company, uh, some may have a question: where does digital fit into my business, right? Is it just a component in some machinery, or it has importance up to the strategy and business level? So actually, digital does fit into two dimensions in company strategy. First dimension is the customer preference. That is why customers choose to buy from you. And obviously, this parameter impacts the business volume or the revenues of the company. Instead of talking in terms of theory and concepts, here is a straight example. Uh, Here in India, we have two types of petrol pumps. Most of them are now modern petrol pumps, which are having digital dispensing, digital billing, and so on and so forth. But at the same time, there are few ancient mechanical type of pumps. And it can be very easily observed that, given a choice, if there are two petrol pumps side by side, customers go to the modern petrol pump, and they do prefer that modern petrol pump over the ancient mechanical pumps. And it has to be noted that the fuel, the basic uh, merchandise which is purchased, is exactly the same. There is no difference, right? So digital does impact customer preference in various ways. Perhaps you can imagine in your industry, if not your company, your industry, your competition, your peers in other countries, you can definitely see how customer preference is impacted by digital. Not only external customers, internal customers like employees, they also aspire to work with industry leaders who are perceived to be more tech savvy and in line with the modern world, instead of working for some company which is believed to be 50 years back as compared to the rest of the world. So in a nutshell, the first dimension in which the digital fits in or is relevant in a company is the customer preference, and the second dimension is the company profitability, typically measured as the net profit of the company. Now, how does digital impact profitability? Well, there are systems which can be classified as decision-making systems, which are basically digital systems, and we will see how they impact the profitability. But the fact remains that these decision-making systems directly impact the company profitability, which is basically taking better decisions based on actual data instead of rules of thumb or intuition. And these are into many areas, the areas of supply chain of planning, distribution, delivery planning, delivery scheduling, operations optimization, plant operations optimization. There are many. We will look into these shortly. So in summary, there are two dimensions which are impacted by digital systems at company strategy level, which is the revenues or customer preference and the profitability. Now, if we now let's classify the so many digital systems available. So digital system for customer preference are typically of the infrastructure type. It has to be noted that typically, right? And simply the examples are ERP, which is recording various transactions, enabling various transactions of the company, or CRM, or at a plant level, it is real-time database system which stores the historical data for years together, right? So for customer preference, typically these infrastructure type digital systems are deployed. They are basically facilitating or enabling the business process which is established. Of course, there are definite benefits of having such digital systems, but it is difficult to assign a money value to these benefits, because these systems are assisting to execute the business process in a much better way, recording the data, providing the data and reports as and when available, providing some visualization, analytics, etc. But these systems are not necessarily altering the decisions made or efficiency of the business process. For example, if there is a CRM, the customer relationship management system of a company, which is facilitating interaction with clients, interaction with customers and keeping records, etc. That system is not necessarily making a decision of saying what are the offers I should launch this season so that I can get more business volume. That is not done by the CRM. At the similarly, let's say the plant level, there is real-time database system. It's having a lot of data. It presents data in various forms, provides some analytics, analytics in sense of visualization, but it does not make any plant decision by itself, right? It doesn't say for today's raw material, these are the plant parameters I should maintain. So in short, the digital systems in the space of customer preference or enabling the business processes are infrastructure type. And now looking at the digital systems for digital system that impact profitability of company are the decision making type. The decision making type systems are like supply chain optimization, scheduling of let's say a product by trucks or tankers in a wide geographic area, that can be optimized. plant operations optimization or particular equipment operation optimization can be optimized. There are established systems like APC, the supervisory control software. Uh, these are decision making type systems. Let's say control system, they are making decision at a very elementary level, like controlling a temperature or something. So at that level it is a decision yeah, how much particular flow is to be altered. So these are decision making type systems. So unlike the infrastructure type, the profitability type, the decision making type digital system do increase the profitability of the company, and these are clear and definite benefits. Even money value can be assigned to these benefits, right? And not only money value can be assigned, there is actually way of estimating how much benefit one can expect if the project is implemented, right? So without even implementing the project, we can know the order of magnitude benefit. In this training also, that aspect is covered towards the end of the training in the detailed part. Okay. So having known this classification, how we can leverage this classification for making better decisions about procuring and utilizing such systems. So when we are faced with current or any foreseeable risk in terms of customer preference, let's say we know that a particular competition company is building a better customer experience, better digital customer experience. There is a definite risk that many of the customers will move to the competition because of better digital experience. Now, to mitigate that risk, some infrastructure type digital systems will definitely help, which will be towards the goal of providing a better digital experience to the customers. But that will be the primary goal. One should not expect increase in profits due to better decision making, because the goal of such system is enabling the work process in a digital way. Um, and there are many vendors available, many resources available. It is a established business. Many standardization best practices are known. It is not particularly difficult to find good partners to install such systems, right? And when we come to decision making type, these are basically to address the challenges of net profit in the company. They are supposed to make better decisions uh, and impact the net profit in a much more positive way. At the same time, this is expertise based area. So there are not many vendors in in this particular field. The systems are expensive because the volumes are not much. Expertise are very few. There is no standardization. Basically, it is an expert's way of doing things. Uh, then we also have to keep in mind that the infrastructure type projects have very low risk of project failure. These are established things and nothing much can go wrong. If something has gone wrong, it is basically the way a business process has been built using that in that software, which can always be changed. And the main success factor therefore remains that someone from the company says that this digital system will do this particular function with existing employees in a much better way than we are doing today. The distinction that is made is it is not the expertise of the vendor, it is the confidence of the company after evaluating that system, that is the main success factor. And of course, other evaluation factors, cost is not very relevant because most probably this is a competitive purchase. There will be several options, but whether it can be used by the company employees, the existing company employees, that is the usability, and can it be maintained over a long period of 10 years or so, that is the maintainability. They are the main evaluating factors. At the same time, the decision making type projects have high risk of project failure because of the high amount of expertise and high amount of uncertainties in the whole project. And therefore the main success factor in such projects is the expertise of the vendor to execute the project. The technology is important, but if you are evaluating vendors which are known in the field, that is not the really criteria, and nothing is visible in terms of technology. It's a software, and all the technology is behind the software, and you cannot really test what is inside. So expertise of the vendor to execute projects is the main success factor in such decision making type digital system projects. And typical evaluation factor should be formal or informal guarantee of benefits. Later we'll see how this can be done in a practical way. Because other parameters, economic parameters like cost, risks are almost irrelevant, because if the benefits are certain, then the payback period is in few weeks and months. So in terms of that, the cost and risk then become irrelevant. The next topic is a digital roadmap and digital strategy. So there are a lot of companies, especially the bigger companies, who insist and actually work out digital roadmaps for a long period of time, let's say next 5 years or so. And they do involve typically industry consultants, or it is an in-house exercise, but the point is they do have a digital roadmap. And although it is an expert subject and it is a time-consuming activity, from a strategic point of view, there are two paths which should ideally coincide at some point in time. Now, one is the well-known road, which is bottoms-up path, where on various platforms, the company and industry experts make a laundry list of available technologies, brainstorm the application in the systems of company, how much benefits will be expected, etc. And then they have some kind of a plan, and they execute various projects, perhaps some pilot projects, and then they evaluate this promise of this technology, application of this technology in the company, and then either continue or kill a particular initiative. So this is a well-known path. It may be done formally, informally, in fragments, or as and when some vendor comes and motivates you to do some activity in their area. But this is a well-known road. The second road is a top-down path. This is essentially a company activity where digital is assumed to be a key enabler in company strategy. In other words, the company strategy does take into consideration that there could be a digital way of addressing those strategic objectives as well. Here is an example. But before that, if some of you are wondering whether digital can actually be relied for strategic business discussion or impact, well, here is one resource. We have published a paper which proves that in a petroleum refinery, up to 1% yield, if it is improved, distillate yield, if it can be improved, it will impact about 20% net profit of the company, and this impact can be done by digital techniques, right? Not only that, we also have going forward in the training case study of a crude distillation unit in a petroleum refinery, where actually a model is built for that plant, and it is run over a period of 2 years of historical data to show how much is the benefit possible. So this is just a digression to make a point that yes, digital can be relied at strategic level, and how it can be done. This is a quick couple of slides example. A simplified example in which we have shown that this is a particular company. They are doing a strategic exercise, and the exercise is basically where the company is now, where the competition is now, and where we expect the competition and ourselves to be after 5 years, and basically the goal being how we will be the winner. Now this exercise is done on various parameters. Here we have shown the customer preference or the revenues, profitability, and competitive strategy. So in terms of volume, I'm sure all of you might have seen or participated in such exercise. So in short, this company says from a digital perspective, there are systems available like ERP and some customer ordering portals. That is the norm in industry. The competition has it, the company has it. One competition is doing implementing some project related to raw material procurement, but not in much information was available. And both the company as well as competition, the business strategy appears to be spreading geographically, perhaps with partners. And the company itself had the same strategy to grow in volume by expanding geographically without increasing any headcounts, and providing the delivery as well as some expert services remotely to their industrial customers. So after 5 years, the company definitely expects that the current digital scenario will continue. Perhaps there will be this raw material procurement platform also, but particularly to meet the goal of revenue expansion at strategic level, some sales management system can it be available, so that managing these partners who are basically remote will be done in a much better and a systematic fashion. And secondly, can there be a system to provide remote expert services and service delivery? So at strategic level, this is identified. The people doing this exercise are not necessarily experts in digital, but they are doing this exercise with an assumption that digital can be leveraged at the strategic level as well. Then there is a area of profitability in which the scenario is the market is comfortable, pricing is comfortable. There is no pressure on pricing right now. But it is expected that 5 years down the line, there will be new competition and price may drop due to competitive forces. And it is realized that although the current prices are sustainable, but if the price comes down by 10% at the current volume, the profit will go down to zero. And where is the opportunity to increase the profit? Is it reducing sales cost, or which area? So the group believed that the most probable opportunity is in the plants to increase yields, right? And therefore the strategic direction for digital function is to find a system that will increase the plant yields, which will increase the profitability by 10-20%, up by that order of magnitude. Finally, the competitive advantage of the company is having quality as a differentiator in market. Of course, the competition is also trying to match the quality, and it is expected that matching the quality is a long-term exercise, but in 5 years probably they will match the company quality. And therefore another initiative to have even better standards of quality and quality ensuring systems, digital systems should be explored. That is the strategic digital direction. Accordingly, from this company strategy exercise, the digital priorities are captured. Of course, the strategic priorities are not met by the digital systems only. There will be several other enablers, efforts, and projects done. But definitely for digital function, these are the priorities which are obtained. So, what is the output for digital function from this exercise? So, on this parameter of customer preference or revenues, uh, although not urgent, but the priority is the urgent priority is sales management system and remote system for service and expert service delivery, and not so urgent is the raw material procurement platform. On profitability, it is the plant yield optimization system, and on competitive, although not very urgent, a new system of quality, including digital system, needs to be developed. So these are the priorities which have come from the top-down strategic approach. Of course, there is parallelly a bottoms-up approach going on, and hopefully this should coincide in the roadmap that is on the paper or minds of people at the right level. Now, coming back to digital strategy, what is the minimum element of a digital strategy? So there are two aspects here. One is the roadmap, which is a very good indication of what is the level of thinking in company about leveraging digital. Now, this is just a roadmap. It is not an investment plan. It is not a project specification document. It is not a blueprint. It is just a roadmap. Like we said, what appears to be the system which we will need as we go along from first year to second year up to next 5 years. And this can be updated as and when things change in the actual business environment. And for such things, it is a new territory. Many systems may not be known even to the digital function in company. There is no standardization. So it is best to leverage the contacts with industry consultants, vendors. There are various exhibitions happening. And all of us know that we do get some formal and informal intelligence on competition. These are all the sources which help to keep the roadmap in good shape of confidence. But if you are not leveraging this ecosystem, then when it actually comes, you may have to spend the most precious resource, maybe the smartest person in the space, to spend time just to learn what to do in this space. So that is the importance of roadmap in digital. And secondly, on the people front, creating awareness about digital systems in average employees, that is the single most parameter which impacts success of utilization of digital system as per many informal surveys, which not only us but a lot of other people have also done. And secondly, there is a particular empowerment to current process engineers or other engineers in digital skills. This is a very specific action, and this is the training about this objective, because these are the people who will be running the company or managing the company over next 30-40 years. And these next 30-40 years are very transformative. The changes are going to be there in large magnitude in digital space. The company systems will transform definitely to a large degree in next 30-40 years. And this training will provide the much needed information and skills which are not taught in colleges even till today. And this training is not to make these engineers as digital experts, but rather how to use the digital systems and digital concepts and digital tools in their day-to-day work. That's why there is no special software which is required to use these techniques. And for demonstrating, we use Microsoft Excel, but of course, any other system, any other software tool which is available can be used. So this is the summary of the training. So basically the roles of owners, general management is covered in this section, and then the bulk of the training is for engineers, including process engineers and other engineers, including procurement engineers. And then last couple of topics are for process engineers. The skills that definitely people will get after going through this training are application of data analytics, elementary data analytics in day-to-day work. Then continuous improvement, decision making, these are normal business functions, how we can employ a digital system to do these things better. Then elementary process modeling and optimization using database techniques without the normal simulation route. Then how elementary techniques to detect abnormalities in the plant very early so that accidents as well as process upsets can be actually avoided. That is a skill which you will definitely get. And then of course the plant performance benchmarking or equipment performance benchmarking, and there will be introduction to the state of art of various digital systems, and some pointers on the procurement and success of such digital projects. And the main benefits are to get the digital skills which are not taught in colleges. Of course, we know the industry constraint that no training should be mathematically heavy, it should be very short, it should be self-paced. One cannot go travel to some place, release the engineers from plant. So all this is addressed in this online training. You will definitely get the digital skills which are much needed but not taught in colleges. And those who undergo this training can definitely be very good resources for success of any digital initiatives, be it strategic initiatives or even in day-to-day work. And company will see higher profits and lower risk of plant operations if many of the engineers are employing these techniques. And definitely with this added perspective of the power of digital uh, in terms of customer preference as well as retaining employees, this can also be seen actually over a period of time. So that completes a topic which is basically for the owners of companies in the process industry space. We will continue a few slides which are for general management, just a little bit of more detail. Um, so this is for those general management people uh, who are actually responsible for this implementing and ensuring success of these digital systems in the company. So here we will discuss about the state of art of various digital systems, what are the key success as well as evaluation factor. We have a framework, we'll present that very quickly. We will talk about money benefits of system. We will not shy away from talking about it, how to estimate, how to ensure, all that stuff. And then of course we will talk about digital ecosystem and couple of slides on our company, how we can add a value in this space. So quickly, just to reinforce, this training is for the roles of owners, general management and engineers, including process engineers in this digital space. And what is the outcome? So basically, application of data analytic techniques in day-to-day work, decision making, modeling, optimization, performance benchmarking, continuous improvement, all these functions which anyway are being done today, how digital can be employed in those. And then what is the state of art, and some pointers on the procurement of the digital systems. Right, and the subject is basically the functions which you are already performing, how digital can be employed. Perhaps there are some functions which are not regularly performed, like performance benchmarking as well as optimization. These are the new things which definitely you can start doing with these new skills. There is no particular prerequisite to undergo this training, but it is assumed that one who's undergoing this training is from the process industry, and they know how the process of the plant, the process of the company and the plant's manufacturing process. Some knowledge about that is definitely there. Here we will not talk about the manufacturing process per se and how it works. That is not the objective of this training. So this topic now, what we are going to talk about for next 5-10 minutes, is for the general management who are actually driving the digital initiatives in the company. They're interacting with the ecosystem of vendors, consultants, employees, owners, and actually influencing the digital outcomes. They are formally or informally maintaining a roadmap, either a documented roadmap or it's a vision, and they are making decisions for investing in this digital space, and of course ensuring the results out of those investments. So when we talk of state of art of digital, which is a very big canvas, we are not talking about individual technologies and what is the advancement in that, etc. This is rather talking about the space, which is how it fits into today's context. We'll shortly see that. Instead of talking about it, we'll talk about what is the scope, what are known applications, what are strengths, how various stakeholders are involved and who can be leveraged, and what are some typical challenges, how we can address those. Now, of course, it can be noted that there are digital systems available for almost every business process, for every business area, for all roles in process industries. So it is not possible to discuss about each individual digital system. So here we'll leverage the fact that these systems can be classified broadly as infrastructure type as well as the decision making type. We have discussed about this just few minutes back, so we will not dwell on this further. But the infrastructure systems are basically enabling or automating the business processes and transactions, but not necessarily making the decisions, whereas the decision making type systems are actually making decisions which impact the plant, which company profitability. Right, and we'll go to that map which we have made as an overview. Of course, by no means this is exhaustive information. A good amount of exhaustive information is available with various industry stakeholders. In this space, there are good market research companies like ARC Advisory Group, there is Gartner, there is Frost & Sullivan, and if you do Google search, there are many companies which are on the internet which do have information and market research reports, etc. Another good source of information is well-known industry vendors like ABB, AspenTech, Aveva, Honeywell, Rockwell, Yokogawa, and there are several others. I'm just giving some examples. However, when you want a specific confirmation about application of some specific technology in specifically your case, the best source remains talking to people, because this field is not standardized, it's not matured. and talking to people appears to be the best way. So this is the state-of-the-art map for digital technologies in process industries. We will go through this. The first row is various business functions and workflows. The second row is about the infrastructure type digital systems available, and on the next slide we have the decision making systems discussion, and then a little bit about the actual systems available. So if you look at it, the first row in white, which is various business functions, uh, one can observe that in all these areas and all these business functions, digital systems are available, especially of the infrastructure type. So if we start with the front-end business functions of demand forecasting, CRM, various transactions which are typically recorded in ERP, this is a very established technology. Large amount of technologies, products, resources, vendors are available, and there is a large amount of industry acceptance also to such ERP, CRM systems, right up to the medium scale companies as well. Um, Going to the manufacturing and manufacturing related areas of planning, scheduling, then actual plant operations optimization, process monitoring. There are infrastructure type systems available. These could be plant systems like control systems or workflow softwares, database softwares, visualization, charting, reporting softwares, scheduling, project management software. These are all available, and they have penetrated quite well. In fact, almost all large, medium, small tiers of industry. Then there are other manufacturing related business functions like operator training, yield accounting, MES systems. These are a bit specialized, and although systems are quite easily available, somehow the penetration is low. The other non-manufacturing systems like commercial, finance, HR, procurement, stores, they have transaction systems like ERP add-ons, and some of the homegrown systems. There is a large availability of systems and large acceptance also. These functions are quite digital as compared to other manufacturing functions. Then there are specialized functions of management, projects, laboratory. Again, infrastructure type digital systems are available, especially laboratory management system, project management software, not so much in maintenance for some reason, but that's the state of the art. But when we talk about the decision making system for the same functions in the first white horizontal row, one can see that either the systems are not available very easily or the penetration is very low. There are not many system at business optimization level, demand forecasting or CRM. They remain to be infrastructure type systems. There are not much decision making systems in this space. In the operations management space, which is planning, scheduling, supply chain management, there are digital systems available, and mega and large industries, there is very good penetration as well. Now, when we come to the actual plant area where the infrastructure systems of control systems are quite established in large, medium, and small industries as well. But if you talk about actual operations optimization or even supervisory control, the penetration of such technologies is low. In refining, there is large penetration of APC, advanced process control, but process optimization, very low penetration. And the specialized work processes of operator training, yield accounting, digital logbooks, MES systems. The systems are available in terms of infrastructure, but there are very few decision-making system, because these functions are not really decision-making functions. These are workflows related to manufacturing. Again, in space of commercial finance, HR, not many decision-making systems are available. In maintenance space, there are some nascent technologies for failure prediction, risk modeling. They are there, but somehow the penetration is not much. Understandably, the technologies are emerging right now, and hence the penetration is not much. And in case of projects, laboratory, there is virtually nothing much in terms of decision-making systems. Now, this is just enumeration of the systems available. Most of you will be aware about it, but in the space of the business transaction, there is ERP, CRM, demand forecasting. In operations management, there are various portals, collaboration, communication, and scheduling, planning type. In the plant space, there are control systems, APC, real-time database, visualization systems are available. Then there are systems available for operator training, yield accounting, MES, digital logbooks, and then there are many for portals and collaborations. In commercial finance HR, the system remains to be ERP and ERP add-ons, and similarly, simpler systems of collaboration, portals, reporting, they are available in maintenance and project space. And additionally, of course, we have project management software, laboratory information management software. And in terms of decision-making system, there's not much in the business transaction space. In operation management, there is supply chain planning, supply chain scheduling, distribution scheduling. These systems are very much available in market. In plant space, there is plant operations optimization, either offline or real time, which is called RTO. Real-time operations optimization systems are available. APC is available very much. And then, of course, there are systems available for operator training, yield accounting, digital logbooks, MES. These are available. And otherwise, there's not much in space in terms of decision-making systems in commercial, finance, HR, maintenance projects, and laboratory. Right now, this is very interesting framework which we have used in multiple scenarios for decision making, evaluation, not only in industrial space but in normal people's lives. So this is very exciting to talk about. So the context here is we are talking about key success factors for digital systems, either for evaluating or for procuring or for accepting or any reviewing any digital system. So there are 6 parameters. They are in red on left hand side. One is effectiveness, then there is usability, then there is maintainability, then there is life cycle cost, typically for 10 years, and on next slide we have risk and head count or company time. And of course, we have to have a separate discussion for infrastructure type as well as decision making type. And depending, the same parameters are applicable differently in these two type of systems. So when we talk of effectiveness, what we mean by effectiveness is the prime objective why this digital system is being put in place. So in terms of infrastructure type, the most important factor is a specific commitment, preferably from the company person, saying that all business processes and functions in all possible scenarios can be done in a better way using this digital system. That is the effectiveness parameters for success of infrastructure type system, whereas in decision making system, the expert saying that yes, this system can be optimized further, it can give further profits. That is what the uh, commitment or formal or informal guarantee has to come from the expert side. So that is the effectiveness, the prime factor in any digital system, digital infrastructure, as well as decision making type. Usability is basically confidence of the company that the system which is being procured in the form it is expected to be, that it will be very easily usable by the existing employees, perhaps with little training, but knowing the uh, the 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 average employee profile, the whatever is the system being procured can be easily used. That is the meaning of usability. And typically it is easy to get feedback from users in initial stage of operation or in pilot implementation. And in case of decision making systems, the number of users are very small because the decisions are made by very few people and they are the users of this system. And as long as a good training is ensured for usage of the system, this usually is not a constraint. Coming to the maintainability of the system over a long period of life cycle, say 10 years, having good and properly worded AMC contracts, including modifications, because this is infrastructure type where the company processes change, company people change, a lot of things change, and modifications is an ongoing activity. So here the maintenance contract, which is typically with the external resources, should cover all possibilities, rates and scenarios. In case of decision making system, the same thing applies because the modifications to the expert system can be done by the expert only. And then the life cycle cost, this has to be visible at the time of procurement, because if some item is missed and not contracted, that issue can become a bone of contention in procuring that item, say 5 years down the line. Uh, of course, in terms of evaluation, is not a very important factor as long as this is procured in competitive fashion. And further, in decision-making type, if the benefits are certain, then the cost, etc., is recovered very easily. So the next important factor to be considered in this framework is the risk. Uh, the risk in terms of effectiveness, cost has been talked about. So what remains risk in this case is basically the continuity. And for infrastructure type of project, the main continuity is the obsolescence of the software or support services. Now, of course, this can be mitigated by specific commitments for 10 years on both fronts. Uh, that can be addressed. On the decision making type, there is a peculiar thing that many decision making type application become monuments after some time because nobody understands what that is. Neither the expert knows that something needs to be done to keep it up to date. And the simple mitigation for that is having an updated functional document in simple English language to which simply says this is the system for that from the point of view of that decision making application, and this is the objective and so on and so forth. And whenever there is a change, that document should be updated and should be given to the expert. Now what happens is typically both people, the expert as well as the person who was in charge from company side, would be changed no sooner than the project is over, and there will be different people, and this will be the continuity, because whatever is the project documentation that is not understood by somebody who has jumped in later from the company side, and if something has changed on the company side, the system side, the expert won't know even if he visits physically. So this simple action can mitigate the risk. And the next one is really important parameter for evaluation as well as for review, as well as for comparing the cost, because many time the cost is compared which is quoted by the vendor, but what is the real cost is the company time cost or any head count which is required uh, to in the regular operation. It is understood that during the project somebody will have to spend a lot of time to build the system. So what is being talked here is really the recurring time which has to be spent just to use and maintain the system. So that's what we are talking about. This is especially a concern in the infrastructure type where the amount of time required could be huge, not so much in the decision making type tools which are basically maintained by the external experts. So this is the framework which we have found very useful because it gives a very good visibility of really important aspect which must be kept in plain view and must be stated plainly. Otherwise we tend to get lost in details and these important aspects are missed. Now let's talk a little bit on the benefit guarantees. We said that this is a very important aspect when it comes to decision making type systems. So yes, the benefits should be known, what to expect from that system, and it should be verified that we are getting benefits to the order of magnitude expected. Now, ideally, every system is different, but there are some evergreen pointers which can always be used in any situation. And the first one is guarantees have to be could be on either of the two parameters, accuracy or the benefit, or it could be on both, depending upon what system we are talking about, what is practically possible. Now, any system, decision-making system, has a model of your system. The model could be different, but it has certain model of your system, and there is, of course, a decision-making algorithm which is completely the works of the expert or the vendor. Now, if the model is good, there is not much which can go wrong in the decision-making algorithm because it's a man-made algorithm. But the model is a system model. There is always a question whether the model is accurate enough for the purpose. Now, in this case, the accuracy of the model can be checked using historical data, and the historical data could be for long time of operation, let's say couple of years, which should cover all modes of operation, all situations in operation, all range of operation. And when this large amount of data is randomly picked up to have 50 or 100 data points at least, and then it is compared, then definitely the accuracy of the system model can be established and concluded. Second thing is, any decision making system is supposed to make decision, and the decisions made in past, which is historical data, can be run again with the decision making system, and it can be seen how much better decisions can be made, and some average value of benefit can be accepted as the benefit which can definitely be expected on an average basis by using the system. So these are the two parameters on which the benefit guarantees could be either of these or both of these. Now, why I said 50 or 100 data points? Because if one has to conclude about the suitability of the system, it has to be a long period of operation, which obviously has to be taken from history. And of course, data can be picked up randomly, but statistically at least 50 number of trials has to be there to draw a very meaningful conclusion. So about 2 years of data and at least 50 samples taken randomly, not from one day, randomly. That is the minimum one has to have. If the goal is to conclude whether the system is accurate enough, whether the system is giving adequate or expected benefit, there is always an argument, like, let's see, this works in the plant. Obviously it has to work in the plant, that is the end goal, and one should have trials in the plant to see whether it works and whether it does give the same accuracy and benefit. But that is like a sample, if it is run for 5-10 days in a plant, it is not going to give any conclusion. At the most, one can conclude that in those 5-10 days what was the performance, but that is not the entire conclusion which can be drawn from such a less number of trials. But it is a necessary activity. Any decision making type of system must be tried where it is supposed to work, be it plant or whatever it is. So that's the note on benefit guarantees, which is the most important factor in the decision making type of systems. And there's no harm in initiating the discussion early in the discussions with vendors in implementing such type of projects. Now, the general management, of course, is influencing a lot of stakeholders, vendors, consultants, employees, owners, and of course there are some silent stakeholders, which is society and government as well. The stakeholders, their key strengths are, consultants and vendors. They are good source of information, not only about technology, for everything related to these digital systems, but one has to take it with a pinch of salt, because the vendors obviously have their interest to push their system, so they could stress some information more and put other information more lightly, which is okay. Similar with consultants, it's rare to find consultants who are very knowledgeable but really independent. But there are some consultants who are really independent. So while taking in the information from consultants and vendors, it should be validated at a gross level using your usual business metrics or other information one has as a matter of regular business intelligence from various sources. The government, surprisingly, is also a driving force in digital. There are some governments who force digital investments. We have seen such a wave in India 2-3 years back. There were huge investments in the industry in digital, and that was a push through government. And as well as societies, those societies who are alert. There have been many instances where society, people living nearby to chemical plants, have forced pollution control and better systems, including digital systems, to be put in place so that the pollution doesn't cause any damage to the immediate environment. So these two, the silent stakeholders, are important to keep tab on, and they can provide a lot of direction to digital system roadmaps and projects, and of course the consultants, vendors, and employees. So now that we have audience of such senior people from industry, your company, we would take a couple of minutes to talk about our company, which is Benchmark, benchmark1.in. So what we can do is we are totally independent consultants in area of digital, particularly in decision making systems, and our value can be summarized in this picture. The top graph is the horizontal is time as usual, and the horizontal graph says a lot of work happens, the efforts are ramped up, and over a period of time then the commissioning happens, and the flat blue line shows that benefits are realized continuously over the life cycle of the project. Now this ramp up from concept to commissioning could be anything between 1 year to 5 years depending upon how new the technology is, how complex the technology application is, basically a long time frame. Now if benchmark gets involved, one thing is this time frame to get benefit by installing some good system gets compressed, and secondly our specialty is we build a model. You don't have to buy any software, but we build a model at our end, and not only we build a model, we start giving manual optimization advice to you, and you can actually start optimizing your systems based on that manual advice. So very early in the project, maybe 6 months, 9 months from concept, you can have actually the benefits realized up to the point where your automatic system does give benefit robustly over a period of time. So what happens is you actually get the benefits of the system, and what's more important is that the project risk is mitigated completely. For any project, the benefit has two risks. One is whether the system really has the potential that one thinks, and secondly, will the particular project will actually deliver that benefit. So once we prove, not only prove, you start getting that benefit regularly, although with manual advice, that risk is completely mitigated. You start getting benefit. You compress the project schedule, because once you know that there are benefits, you can take certain risks, you can expedite, and you can have the system in place very quickly. And we continue to engage with you in the other phase, in the further phase, where during the normal operation of the automated system or more robust or more standard system put into place, we can provide periodic audits where we can continue to verify that you are getting the benefits which are supposed to be gotten by you. So thus you start getting benefit without spending even a single rupee or a single dollar on actual project, right? And same thing, we can get involved to assist you for acceptance or validation of the project benefits, which is an important milestone. Now, if, a small example just to reinforce the same thing. Let's say there is a small project for a particular plant in a refinery, real-time optimization project, which is going to optimize the particular plant operation lifespan of 10 years. The benefit expected is 15 crore rupees, or over 10 years 150 crore rupees. The red figures in are in US dollars. So benefit expected is about a couple of $1 million per year, and a total of about $20 million over 10 years. One-time cost is 8 crores and 10-year maintenance cost is same. So in total, a couple of $1 million one time as well as maintenance cost over the life cycle. And project duration is 1 year of concept to procurement and 1 year of actually doing the work and commissioning, so about 2 years. And the risk, what are the risks? Risk is there is always an estimated benefit. Is it real? Can we confirm it? And will the project deliver benefits? That is another risk. And will the project continue to deliver benefits over the life cycle expected of 10 years? These are the known risks. So the top row in white is typically how the project would have happened over a period of 2 years: conceptualize, business case, procurement, project activity, commissioning. Then you start getting benefits, and you continue the benefits over the life cycle. But when benchmark gets involved during the conceptualized phase itself, benchmark can assist you to prove the benefits based on a model. Not only that, you will start getting the benefits immediately, although in a manual fashion, and your procurement project activities can keep happening, and even if there are a few delays, it doesn't really pinch, because you are already getting the benefit. And once the project is commissioned, benchmark can independently validate the system benefits, as well as periodic audits could be conducted over the life cycle of the project to ensure that the benefits which are obtained are up to the mark. So what is the result? One is the risk is mitigated of project, whether the project has potential to give benefit, that is completely mitigated, and the benefit realization starts maybe 1.5 years before you spend anything on the software, and then software or the project, and then of course the benefits are ensured to be realized over the life cycle of the project. So that's what we can bring to table for you. So we have talked about this. There is another way of quantifying the benefit which can be obtained by benchmark involvement, which is in this highlighted yellow. Basically, if the time cycle of the project is compressed by say 1 year, then you start getting the benefit 1 year in advance, which is about couple of $1 million or 15 crore rupees benefit. And if you want to quantify the risk of benefits, 150 crores or $20 million is the total benefit expected, and let's say there is a 10% probability of failure, which is mitigated by by benchmark, by proving the benefit well in advance of procurement of the software itself, then that risk is around couple of $1 million, 15 crore rupees. That also can be seen as a value provided by benchmark. So that was the small example about benchmark. That completes the session for the owners as well as the general management of the company. And now we have a longer session, which is basically for all engineers, including process engineers, and the examples are mainly from process industry. And we will go at a bit slower pace because these are technical concepts and should be appreciated well once. You are not going to watch this 75 times, right? So we will start with this. So my request to all is to have a pen and paper handy, no computer please, for calculation or using any software. You can have a calculator if you need help with basic arithmetic operations, and we will get started. But before that, why there is so much of talk about data analytics, as compared to 10 years back? Is this something new, some new discovery which is there? Answer is no. Data analytic techniques are much more than 50 years old. I have personally been using some of these techniques. I remember using 25 years back as well. And what data analytics requires is, of course, the data analytic techniques, but it also needs domain knowledge, and most importantly, it needs data. Now, what has happened? The availability of tons of data, and that too cheaply and conveniently, is the new thing which has happened in last 10 years. If you remember, before that, even the plants did not have any data sources. The business functions did not have much data. That's why the data analytics has taken off now. The main thing is availability of the data, and that too tons of it. And therefore now data analytics has come up as a very good alternative or complementary analysis technique, in addition to whatever engineering analysis people have been doing. Now this is a large section. We will not discuss the summary. Please enjoy the complete learning. Just to start a bit of warm up, recently, couple of days back, I saw a news item on this. It says oil and gas industry seeks AI talent to harness unstructured data. So this is something related to the subject. It talks about few things, and at the end somebody has commented that unfortunately this data is often not captured or aligned, leading to significant lot of potential insights and hindering automation efforts. Now this training will definitely address this concern, and you will be definitely able to reduce that significant loss of potential insights, and hindrance will be removed from automation efforts. Another apprehension a lot of people have is, why we have lots of existing tools. We have simulators, we have APC, we have this, we have that. We already have a lot of methods. So the answer lies on two fronts. One is accuracy and second is suitability. Accuracy we will discuss in detail in technical terms later. But at a concept stage, even if you have, let's say, simulation model or whatever method you are employing, you try to match the models with the actual plant results, right? And what are database models? Database models are made from data itself. So they are already matched with the plant, and therefore they are much more accurate than the non-database models or first principle models. Secondly, now really compare from the point of view of engineers in a chemical plant who are working in a plant like process engineers. Now the situation is they are not designing a plant. The plant is already designed, not only designed, it is fabricated and working. That too working in a strict range of parameters, for safety purpose or for standard operating practices purpose. There is a strict range of parameters in which the plant is operating. Now, here the database models are more accurate and more relevant in this small range, right? Thirdly, the database models, especially the simple models, we'll see what are simple models and complex models. So the simple models are very easy to build. They are very quick to build. In few minutes you can build these models. And these models do not need any thermodynamic data, kinetic data, transfer process, mass transfer coefficient, etc. All these are not required, which are usually the constraints in making very rigorous simulation based models, right? So the rigorous model, the simulations, tachometric, such models are more suitable for design and global type of analysis. Like what is the base operating pressure for ammonia plant loop, based on kinetic and thermodynamic data and realities. And based on that, then suitable equipment will be designed later, maybe compressors and the pipelines for that high pressure, or maybe catalyst will be thought of. So all these things, the rigorous models are for that. Accuracy is not the main advantage of the rigorous models. Whereas in the scenario in which a plant is already fabricated, working within a short range, the database models, they give a good balance of efforts versus results. You spend few minutes making the model without any thermodynamic or kinetic data and use those accurately. So having said that, I think there are no existing concerns about why we need to learn the subject. Of course, we will see the particular value as we go along. Now, what exactly will be the change in you? And let me make this bold statement that this training will change the way you look at the world, right? Particularly from the way you look at the numbers and you make sense out of it. Now, here is an example. I'm sure you have seen a lot of WhatsApp forwards. So this is one of the WhatsApp forwards which came to one data analytics guy. So it is basically saying how India pays. India pays by paper money, UPI, NEFT, and credit cards, and so on and so forth. So what caught his attention was the UPI versus paper based. So in India, we have been using paper money for long time, and UPI is a recent phenomena, typically after COVID, that is year 2020, about 4 years back. And it shows some numbers. It says what is the volume of transaction for paper as well as UPI, and it also says by value what is the breakup. So that data, maybe this is a bigger picture. Hope you can see the numbers. Maybe you can pause and have a good look at it. And then this guy replied on that group that, it is very interesting. It is implying that the value of average paper money transaction is 60 times the UPI transaction, right? That means general public has almost stopped using paper money for small transactions like, grocery store bills and so on and so forth, and only high value transactions are happening in cash. That is the definite conclusion one can take out from this data. Well, almost everybody said, can you explain? I don't understand. So here is the answer. 0.6% transactions are cash and the value is 10%. So average value of cash transaction is 10% over 0.6, whereas the similar cash transaction UPI transaction value is 20% over 70. And then if we have to know what is the ratio of this transaction, that is cash transaction average value over UPI transaction value, we can simply divide these two, and I didn't even bother to divide. It is approximately 60 times, right? So that's the conclusion one can draw. Now data is same, but the conclusion is different, and a good pointer is conclusion is as good as question, right? When a lot of people are looking at the same data, the right question should pop up in one's mind, then any technique, including data analysis technique, can be deployed. Now, the calculation that I shared with you is nothing difficult. This is not data analytics. It's just high school, ratio proportion calculation. The approach is what matters. Technique can keep changing. Today it is data analytics, but the approach is what one has to practice, and data analytics is the right tool to practice that, because all you need is approach and data, right? You don't have to know a lot of science behind it. Of course you have to know the concepts, which is called as domain knowledge, but the conventional engineering calculations don't need to be followed. Conventional engineering, thermodynamic, kinetic data need not be available. So next what we are going to do, hopefully very quickly, is we are going to review some elementary, that is simple data analytic techniques. Now this course is basically for application of data analytics, but it is possible that many may not know these simple techniques as well. And even if you know these techniques, perhaps we have not looked at these techniques from a process engineer's point of view. So please do spend some time in listening to this, and then we will go to the application of data analytics, right? So as said before, the goal of this training is application of data analytics, and we are going to first have a quick review of the techniques themselves. Now what do we mean by application? So basically there is a problem in front of you in the plant, and you know the standard way of solving it using thermodynamics, kinetics and stoichiometry. But if you want to apply data analytics, what we basically mean is defining the problem in a different way. Same problem, but defined in a different way, so that it can be solved using data analytics techniques rather than other techniques. Now all of us know that we have a plant and we have a laboratory, because whatever are the process streams or products, their properties cannot be calculated with reasonable accuracy using engineering calculation. That's why we have the lab, right? Otherwise we won't waste money in building labs and equipment and having people to run those experiments. But if you define the same situation, that can a correlation be found, based of the measured plant data, temperature, pressure, to calculate the product or stream property, right? So we have defined the same situation in a different way. And the answer is yes, it can be done, and it's very simple to find a correlation to predict a property. We will see that in a few minutes. So this is what we mean by application, and this is how a practical example of how to define a problem and then how to solve it. Now, believe me, there is not much mathematics, there is not much of statistics, but this is just one slide on statistics. Please listen to this. You probably already know this. So when you see any data, the data is of course varying around an average value. So everybody knows average. Another statistical quantity is standard deviation. I'm not going to tell you the statistical definition of standard deviation. Basically, the total range of variation of parameters, if you divided it into 6 parts, then that each 1/6 of a range is called as a standard deviation. All right. So over the average value, there will be 3 standard deviation ranges, and below the average, there will be 3 standard deviation ranges. And there is something called as normal distribution, which says for any data, the 99.7 or practically 100% data lies within average plus minus 3 standard deviation range. And if you take average plus minus 2 standard deviation range, about 95% data is found in that range. And if you take average plus minus 2 standard deviations space, you will find 68% of data there, right? And average standard deviation are calculated by Excel or any other similar spreadsheet or simple statistical tool. Now, this can be explained using process engineers language. Now, imagine any parameter, measured parameter in your plant. If you are working in a plant, it's very simple. If you have worked in a plant 10 years back, just remember your plant and just remember any temperature that you are familiar with. Now, this is what natural law is, that if you take 10 readings of that parameter, let's say it's a temperature, okay, and you have taken one reading every 1 hour, so there are total 100 readings. So this law, the normal distribution law, says that obviously there will be an average temperature, and if you go into this fashion, we will take an example that will make it simpler, right? It says typically out of those 100 data points, 34 will be, in this plus minus 1 standard deviation range typically. Then 13.5 or 13.5% will be in the next range, and 2.5% will be in the final range. In simple words, the average plus minus 1 standard deviation is called as typical range. Few times the data can be seen in a range which is more than that, and rarely the data can be seen in the extreme range. How rarely? 2.5%. Okay. This applies to each and every parameter in your plant. It's a challenge. Next time you go to the plant, just take known number of data points and just check the number of data which lies in this range. Okay. Now let's take an example to see utility of this excuse me, this natural fact. Now, when you walk into the control room, let's say on one day you see a chart like this. So this particular parameter, the black are the limits or range of the parameter. So you see that in the last 8 hours, the parameter has been within the range, but there was a ramp up of the parameter for about 1.5 hours, and then for past 4 hours, the parameter is at a higher but within the limit range. All right. Now let's spice it up with some numbers. So let's say this parameter is TI101.PV, which is basically a product temperature after product cooler. The average temperature is 100 degrees Celsius, and the typical range of this parameter is from 88 degrees Celsius to 112 degrees Celsius, right? So today the plant is operating normally, right? All other parameters are normal or typical or usual, and this particular TI101 value has shown the chart like that. That is, today this temperature is 111 degrees Celsius since last 4 hours, and 111 degrees is definitely within the limit because the range is 88 to 112. And of course there is no alarm like TI101 temperature high or something like that on the DCS screen. Now if you look at the chart on the right hand side, these numbers we have translated into a chart which says the average temperature is 100, and if you go one standard deviation above, the temperature will be about 104, then 108 after 2 standard deviation, and after 3 standard deviation the temperature limit is 112. That means if you have a temperature above average, but if it is between 100 104, it is typical, normal, usual, there is nothing appreciably different about it. Few times even it could be around 108. There could be some phenomena happening in the plant which is not detected or measured, but it is still not an abnormal, nobody will feel anything abnormal about it. But if the temperature is above 108 times, it's only a 2.5% chance that the temperature, that is, it could be rarely there. Okay, so if it is there has to be some reason, right? Now the question is, the process engineer is on a daily process monitoring visit to the control room. Typically this doesn't happen now because they can see the data in their office only, but let's say is there. Now should he investigate so as to why the temperature is high, or just leave it, because the temperature is within the range and not really rising? Now just think for a minute and make up your mind, right? And here we go. So the explanation is like this: as all the other plant parameters are normal or typical, that is around average, the product temperature should be around average, right? The whole process is connected, and if everything is normal, this temperature has to be normal. But if you see the chart, and around average means typical, plus minus 1 standard deviation. It could also be plus minus 2 standard deviation because of some phenomena which are not observable or not measured. But the temperature is actually in the rarely zone, the temperature can be there very rarely, right? It definitely cannot be called as a usual occurrence. Now if it is in the rarely zone, it should have a detectable reason. For example, the cooling water that cools the product, that cooling water temperature could be higher than usual, maybe due to some issue in the cooling tower, right? Therefore the process engineer should investigate why this temperature is rarely high, although within the range. But of course, if nothing can be found in reasonable time of few minutes, at least the operator should be flagged that this temperature is rarely or unusually high, although within range, to check whether any other abnormality is seen in the plant. So the purpose of explaining this was to assimilate this concept of normal distribution, and in plain English it means any parameter in the world, it follows normal distribution, that is percentage of data around average, right? Or what is the chance of a parameter being at a particular range around average, whether it is in typical range, almost typical range, or rarely range, right? If that uh, concept is in the mind, one can see more than data what others can see, right? So this the same thing which we have plotted here, and this can be for any plant, any parameter. Now, one minor question for you: what is the correct range of a parameter and how to find it, right? Most people will say design data and so on and so forth. Yes, parameter ranges could be mentioned in SOP or licenser's manual, but these documents, could be irrelevant due to multiple revamps. The plant was installed 30 years back and there were 8 revamps, so many parameters are changed, many ranges might have changed, or maybe these documents are simply lost. If you are particularly in a plant, you may not find these documents. And for the same reason, please do not read the range mentioned in DCS or control system in the plant. Many times it is not updated. Somebody put it 30 years back and it remains to be there. So when somebody wants to know what is the normal range of variation of a parameter, don't take the DCS range, don't try to look for manuals. This could be wrong, being very old. Secondly, range can be found, the best way is from historical data for a long period, let's say 2 years or so, or 1 year. Of course, here we have to see that the plant is not having any blocks of operation. By blocks, what we mean is some plants have different products over seasons, right? Or as per season they are having different operating parameters by choice. So these are different blocks of operation, they should not be combined. So if you have to take a range of a parameter in summer, and if the plant is known to have different mode of operation in summer and winter, you should look for the summer data to see what is the normal range. That's the meaning. Now again, if data is not available for some reason, it is not historized or something, just ask 3 experienced people and take average range, whatever they say. Of course, one can do some calculations and simulation, but that probably is not the fastest way of doing it. But remember, range we have to know for every important parameter realistically. It is an exercise worth doing. Right? Now, one more example why it is important. Right? So, in a class there are 120 students, right? And in a particular exam, the scores of various students are from 19 to 91%. Now, one particular student, Rambo, he has scored 78% marks, and not only that, he has ranked 4th in the class. And he thinks that he's one of the toppers in the class, and it's just bad luck that he is not the topper, right? Now we have to see whether his thinking is right. Now if we plot the same data, the average of this score 19 and 91 is 55, right? And these are the plus minus 1 2 3 standard deviation. So above average is good score, better course is one more standard deviation, and the best class of scoring is the average plus that 3 range, standard deviation range, which is from 79 to 91. Now our Rambo has scored 78, which is just below 79, right? So he is in a better class, right? He is not in top class of the class, right? So if somebody asks, is Rambo in top class or he is just better than many students? And more importantly, does Rambo have any room? Should he have any motivation to improve further by studying harder or better? to be in a next class? So the answer is clearly yes, because although he is much better than many, he has ranked 4th, but he is not really in the best class of students or best class of people who are scoring in this exam. So there is room for improvement, there is room for achievement, and it is worth doing the effort, right? So the point of this example was, this is day-to-day life. It is not chemical engineering, it is not process plants, it is day-to-day life. And if the concept of this normal distribution is in your mind, you can make sense of many things in life as well as technical situations. For example, there is something called as bell curve. When they decide how much salary increments you should get, it is nothing more than this. It is the same stuff, right? Now, with this little background of some basic statistics, we will go to the simple techniques of data analysis. See, these are the techniques. There is no suspense. One is simple regression, sorting, charting, which is basically finding relationship between two parameters, x and y. Multiple regression is finding an equation, linear equation, to predict parameter y from, say, n number of parameters. Then there is single variable optimization and multivariable optimization. We will see all of this. Some of you may know this. The incentive for you to listen to this stuff is, this is more from a process engineer's point of view, not from a statistical class point of view, right? And while going through this section, you may find a lot of new information, a lot of exciting techniques, and you may want to just quickly open your computer and start playing with some data in Excel, some data from your plant, and you want to immediately do something. Please refrain from doing that. This is not a very long training. I request you to please focus. That will give you the right approach. Playing with data in Excel or some other software you can do at any point in time. I request you to focus here. That's the same reason I have not used actual Excel here. I use these snapshots so that we can discuss more and play less. All right. Because our end goal is to apply these techniques, right, and apply it in your work. And that's the skill even data analysis experts won't have, to apply these techniques in your work, the work that you only know. Right, so we start with this usual example where a lot of people feel excited in the first place. Now, if I tell you, just look at this chart. This is chart of any two parameters. If you have seen DCS graphics, if you take a trend and just put two parameters, you see something like this, right? You see variation of both the parameters. And as chemical engineers, we are always presented the data in this fashion. The x-axis is the time and the y-axis is the value of a parameter or a set of parameters, 2 parameters, 8 parameters, or n number of parameters. That's the way we have been looking at data. But if you take the same data, please listen to what I'm saying. You take the same data, right? Nothing different. And take the data and just sort it, right? You know what sorting is. You sort x, you sort y with respect to x. You take out the time axis, just have x and y and plot them against each other. What you see here, there is a perfect correlation. If you know the value of x, you can find the value of y. But remember, the chart you looked at, you never felt that there could be any correlation between these two parameters. That is because our brains have been configured to see the data in that time series format, right? We never think that we can take data and find out if there is any relation. Obviously, this data was manufactured by me, but after it is put in a random fashion, it just looks like the chart which you saw. Now also observe that this is a chart of X versus Y, two parameters in the plant, and the equation of this line is written on the chart itself, and there is this another parameter called R square equal to 1. So this is called as coefficient of correlation. I will of course not give you the statistical definition of this. The process engineer's meaning is, if R square is equal to 1, that means the equation can describe the total variation. Each value of Y can be calculated using the corresponding value of X. That's the meaning of R square equal to 1. If R square is equal to 0.5, that means only 50% of Y's can be calculated accurately from Y using this equation, and 50% of the time the Y's will not be accurate. If R square equal to 0, that means there is no correlation between X and Y. They are behaving independently, and there is no equation that is existing with which you can calculate the value of Y using X. Got it? And the equation itself is just Y equal to mx plus c, which is the line equation of a line. So this is the sorting or XY graph or a simple linear regression. The sorting can be done using any tool, any spreadsheet, definitely using Excel. If you have not done that before, let me just in few seconds tell you how to do it. So this is the data I used for charting X and Y. Okay, this is just random X I have generated and just multiplied by 2.5 to get the value of Y. That's why there is a perfect correlation. But since the X is random, Y is random, the chart looks like this. And if you have to sort, you have to just find out a tab called data. The main tab called data, file, home, insert. In that there is a tab called data. So obviously you have to select the data, and then in the data tab there is a sort tab, and when you click on the sort you get this dialog box, and then you can select how to sort the data, right? And then you can sort it. For example, I want to sort on X, so I will have to select the column D, sort by column D, and cell values from smallest to largest. Then I will get the chart that we have seen before. Okay, or you can simply put XY chart. So that is, you select the data, and you in the tab of insert there is a sub menu called chart, and then you select the XY type of chart, and once you select the XY chart of type of chart, you get this equation, and when you right click on this line you get this format trend line graph dialog box, and at the bottom you can see these two options have been checked: display R square and display equation. Once you do that, you just simply get the equation and R square on the chart. Alright, so the takeaway is, if you have two parameters X and Y, temperature and pressure, reflux and top temperature, whatever it is, and if you want to find a correlation between these two parameters, you just take the data and draw XY chart. You will get an equation, you will get a line, and you just right click, and in couple of clicks you get the equation as well as R square. Right, so R square explains how much of the variation is explained by this equation. Now, from a statistician's point of view, they use R square in a different way. If R square is close to 1, they say, oh, my correlation or my equation is good, I don't have to spend any more time to do this model again. But if the R square is less, then they think they need to do some work, maybe check the data and so on and so forth, so that the R square comes closer to 1, or they have to declare that the data is not correlated. There is not really a physical relationship between these two parameters, and therefore the equation, although you can get a numerical equation, it is meaningless. It cannot be used to predict the parameters. I hope you get it. The purpose was not to teach you how to draw an XY chart. The purpose was to use to show you one, the approach, that always you need not look at the time series data. Sometimes you have to plot in a different way, or sometimes you have to look at the data in a different way. And the second is what is the meaning of correlation equation, and what is the significance of R square from statistician point of view, and as well as from the process engineers or any engineer's point of view. All right, hope this is understood. Then we'll go ahead. Before we go ahead, we talked about blocked operation of plant some time back. Now this is a chart of that operation. The bottom data is, let's say, summer data, and the top data is winter data, right? But if we don't know the process part, we are just calculating statistically, we may get an equation which looks very perfect. The line looks very perfect. Anybody will say that this is a perfect fit of a line, for the given data. But if you see, the R square is 0.4, right? What it means? So although it looks to be a perfect fit for the given data, it means only 40% of the time you can calculate the value of y using this equation, and using the corresponding value of x. That means this equation is not very reliable. And we know the physical reason why it is not reliable, because these two are different modes of operation. And what you need to do is just select one data, right? This bottom data, if you select, you fit one equation here, then you select the top data separately and fit a new equation there. Then you will have an equation which will have a very good R square value, closer to 1, and that equation can predict y very accurately. Excuse me. Okay, so accuracy of prediction we just touched upon. Later we are going to dwell on it quite a lot. Okay, now this is another sorting, right? I will tell you what it is. This is the blue line is the yield of a plant, okay, and this time frame is about 2 years. So this yield of the plant is the actual yield from data, and the top the red data is the model predicted yield of the plant. Now without any numbers, I have not kept any numbers here, you can make out that the model predicted optimized yield, I'm sorry, not just the yield, it is optimized yield. The optimizer suggested a higher yield, and you can see that the optimizer suggested yield is typically on the higher side on the actual yield, right? Okay, right. This is another example of how charting gives good insight. So in the last example, the reason to show the optimizer yield and the plant yield was, without the time parameter, the charting shows what is the comparison between those parameters. Now here again, you might have seen the charts like which are on the top on left hand side. Typically people present model results as a comparison between actual and model. Here the blue one is the actual and the red one is the model, and typically a lot of people feel that this is a very good fit, there is absolutely no error. But you take the same data and plot it in a different way in a XY format, you can see that there is a random error. Okay, there is error, and not only error, it is random error between the actual and the predicted. And you can even see the magnitude of error, what is the error that could be highest in the given data, right? So simply a different point of view can give a lot of insight, right? And in terms of data and charting, it means instead of a time series, if you take XY plot, it gives you a different point of view, different insight. So we have already talked about simple regression, which is the equation of the type y equal to mx plus c, or the relationship between two variables y and x. But many times in process plants, the y depends on several parameters, not only on one plant, only on one parameter, right? So if you take product property, it doesn't simply depend on, let's say, the temperature in the equipment. It depends on the concentration of various streams. It depends on pressure. It depends on level in the equipment, so on and so forth. In short, a parameter depends on several independent parameters. And of course, we can have an equation of the type y is equal to, if y is a function, depends on x, y, and z, we can have an equation of the type ax plus by plus cz plus constant. Again, a, b, c are constants. Thus, you can predict y if you know various values, corresponding values. Let's say at morning 10 o'clock, you know the value of x, y, and z. And if you have this equation, you can calculate the value of y at 10 o'clock in the morning. You don't have to send a sample and get it from the lab in the night, right? So such type of equation can be obtained by a technique called as multiple regression. Now we will just see that technique. So this is an example data. So this y is the parameter which we are interested in predicting. Let's say this is some lab sample result, and these are x1, x2, x3, x4, x5, x7, x8 are plant measured temperature, pressure, level, etc. And what we want to find out is an equation, right? So we want to get an equation to predict y as a function of x1 to x8. So it will be like, I'm not going to read out, it's going to be like y is equal to ax1 plus similarly up to x8, and then there will be a constant. So so basically finding an equation means finding the value of this a, b, c, d, e, f, g, h, and that constant, right? So if you find these values, then we have the complete equation. Now we will see this. This technique is called as multiple regression, as some of you might already know. And what we are going to do now for a few minutes is to demonstrate how this equation can be obtained or identified using the given data, right? Using Excel, that too a simple function of Excel. There are advanced add-ins available, etc. We are not going there. Just like you have the function of average, sum, etc. There is a function called linest, line estimate, perhaps that's why it is called linest. With this function, you can find a multiple regression equation, and that is an equation to predict a parameter which has several independent parameters. So what you do is, we saw that data, right, y and x1 to x8. So just below that data, you select 5, 6, maybe 6, 7 rows, and the columns equivalent to the length of the columns of y and x data. You will know why we are doing this in a while, right? And after you select this range, then you go to the formula bar and type linest, and then you give the various inputs. All right, some of you must be using Excel regularly. If you have to do sum, that's what you do, right? Equal to sum, and in bracket you give the range of numbers where you want the sum. So similarly, we have given a linest function, and then it says give the values of y. So you select the y range, then there is a comma, then you have to give the X range, which you have to give the complete X range, which is in pink here, and the options you give true and true. If you see help on this function, you will know the significance. Just for the sake of speed and saving time, I'm saying that just say true, true, select true, true, close the bracket, and usually you will press enter. So here is the tricky part. You cannot just press enter. This is an array formula. So instead of enter, you have to simultaneously keep the shift and control key pressed and then press enter key. Okay. So mechanically, instead of enter, you have to press shift control and then enter. Now the explanation is this is not a simple formula, this is an array formula. That's why you have to use this. In the help you will find further explanation. Now this is the output, right? You see few numbers down there. So this is the equation which is found by Excel. So you see the equation is on top, y is equal to ax1. So a is the constant corresponding to x1. Similarly, b is the constant corresponding to x2 and up to x8, right? So h is the constant corresponding to the parameter x8, and of course there is a common constant. Now this is the formula result. This is the equation found out by Excel by using formula LINEST. The only tricky part here is the sequence of constants is different. You would expect a to be the first constant, but actually it is the last constant, which is h, then the second, which is g, and so on and so forth. The order of this constant you have to note. It is exactly in reverse, and the last number, that minus 1.281 etc., that is the total constant in that equation. Got it? Right? So it is so simple to find an equation. Perhaps there are simpler ways, but I wanted to demonstrate this, which is the simplest even in Excel, and that's what I also know, which my mentor taught me 25 years back. Right? The second thing, we have seen the R squared value for a simple regression or the XY chart, which was the quality of the model for X and Y. Now this Y versus all the parameters also has a coefficient of correlation, and in this case it is 0.96, right? Now this is also a very good equation. That means 96% of the times Y can be calculated very accurately using the values of corresponding X1 to X8 and using this equation. Okay, if this R squared is 1, that means all 100% values can be predicted accurately using this equation. Got it? You would have many questions in your mind, but this is not a Excel or a statistical techniques course. I request you to please open help in the Microsoft Excel or whatever tool you are using, and you can read complete information. It will explain all these unanswered question in your mind. From a process engineer's perspective, you need an equation to predict a value which depends on several parameters. It can be simply done if you have enough data, and not only you get an equation, you also get a parameter which explains the quality of the model, right? Now many times you have heard the word accuracy. So particularly when you are talking about database models in process application, process engineering application, it has a specific meaning and it has a specific significance. The R squared value is given a lot of attention by statisticians because they don't necessarily know the process, physical process, chemical process which has generated this data, and they just go by the quality of the model. Whereas that is not enough for the process engineer. What the process engineer really wants is the accuracy of prediction. Okay, we will explain this with example, right? So even if you have good R squared value closer to 1, that doesn't mean the model is very useful for the process engineer, right? And let me tell you, accuracy we will define as the maximum error. If you see the graph on the right hand bottom side, the maximum amount of error, the red part, that is the accuracy or the error of the model. You know, there are times when the model is very accurate, but you have to take the maximum error as the whole model accuracy. That's the reliability of the model. Now, why accuracy is very important in process engineering applications and not just the R square? Now, imagine a lab measured parameter in your plant, which is being calculated by a model. Now, this could be a ASTM distillation point in a refinery, or a liter weight in a cement kiln, or it could be a kappa number in a paper mill, or heat rate in a power plant. Whatever it is, some lab measured or complex parameter which is being calculated by a model. Now this parameter obviously has a range, and that range is shown in the black thick lines, the lower limit and the higher limit. And let's say this blue dot is the current value, and the range is shown here, right? And imagine what the process engineer has to do. Depending upon the lab result or the model prediction, the engineer has to take decision for action. Now, what is the action? Whether to increase temperature, pressure, some other parameter, to move this important parameter either up or down, right? Now, if the blue dot represents the current value of parameter, and let's say it has come from lab, then the engineer will not do anything. Why? Because the lab value is the ultimate truth, and it is within the range, so engineer doesn't have to take any action, right? Now, if this model value has come out of a model, and that model is known to have a error, that error is shown by these double-sided solid red arrows, right? That means even if the model is predicting the value of the parameter as this blue dot, it could be as high as here, or it could be as low as here, right? But still the parameter is within the range, and therefore the engineer will not take any action, right? Because the engineer knows that this value, the parameter value, has not come from lab, it has come from a model, but the model is reliable to have known error of only this magnitude, right? Understood? That is the significance of accuracy or error in a given model. Even if it is a simple model, y equal to mx plus c with a very good R squared, but if the accuracy is reasonable, then only it is useful for process engineer to take action based on prediction of that model. Now imagine if there is a large error, whatever be the R squared value, if there is a large error in the model, let's say the error is of the magnitude which is shown by this broken red arrow on the left hand side. So what does the engineer know? The engineer says, I have a model which is not very accurate, it has a large error, and it has calculated a value of this blue dot, but I know that the error could be as high as this dotted arrow, right? So the actual value could be lower than the lower limit. You know, this here, if you go by the highest error on negative side, or the actual value could be as high as touching the higher limit, if the error is positive on the positive side. Now, based on this model output, what action can the engineer do? The engineer doesn't know whether the parameter is below the limit or above the limit, right? Although the model is predicted blue dot, the engineer knows the error magnitude of model, and therefore the actual value could be much below the lower limit or almost at or little higher than the higher limit. Then the engineer cannot take any action because he simply doesn't know whether to move this parameter up or down. Got it? That is the significance of model accuracy in process plant or process engineering. Especially when you are taking decisions in the plant. We are not talking about design calculation, that's a different field, different application, it has different yardstick. We are talking about actual plant operation, and that is the significance of accuracy. So now you know why you have to plot actual versus model prediction, find the error magnitude, and then make the error magnitude known to the engineer who's taking decisions. Right? R square means nothing to the process engineer while taking decision. All the process engineer needs to know is the confidence on model in terms of accuracy or error of magnitude. Got it? Please keep this in mind. Right? So we have already discussed this. Now, the next question is if you are developing model yourself, or there is some expert who is developing models for you and giving you the models, what should be the accuracy of the model, or what should be the highest error in this model? As a rule of thumb, the error should not exceed 1/10 of this range of parameter, right? If the error is too large, the model is not useful. We have seen that very clearly 1 minute back, right? But this, of course, is a rule of thumb. You can have more accurate model, or you can even accept less accurate model depending upon the actual ranges and values of the parameters. But as a rule of thumb, the maximum error should not be more than 1/10, or accuracy should be at least 1/10 of the range. And how do you find accuracy? You take a ton of data and you calculate the predicted value from the model. That model could be simply y equal to mx plus c, or it could be a complex simulation model, or it could be anything. For a process engineer, if he wants to check accuracy of the model, it is very simple. You take a lot of data, you have predictions from the model, and you plot those predictions against actual values and see what is the error. If the error is more than 1/10 of a range, there is a question mark on utility of the model. You have to look really hard whether it can be used or it should be discarded. Okay, so that is R squared versus accuracy. So for a process engineer, especially working in a process plant, accuracy is more important. Right? Now, for optimization, it is further more important. So optimizer take decision just like an operator. I have to move this parameter from the current value to the limit value. Whereas if there is control or even APC, advanced process control, the set points are given in a range of very small magnitude. Let's say 1/100th of this range, and those changes happen over a period of time very slowly, looking at the dynamic response of the plant. So the accuracy is very important from optimization point of view or taking the decision by process engineer. whereas automatic control APC, the model in that uh, program could be little less accurate because they are taking the action in very small magnitude and checking the effect in real plant and changing the direction of control, right? At this point in time, all you need to know is accuracy is very important for process engineer whenever either process correction is being talked about or process optimization is being talked about in an operating plant, right? So in our workshops, this is the exercise which we do, and I can request you to do the same right now with your pen and paper. So you can write down some important parameters in your plant. Forget that there is any model or not. Assume that there is a model. Then what should be the accuracy of that model? If anyone builds a model for you to predict that parameter, for that you will have to know the typical range. And if you remember, we had a discussion on the range some time back, which is finding a range is also an engineering activity, right? So assuming that you by now you have found out range of all the typical important parameters, then what is the minimum accuracy required or maximum error permissible in any model? It could be y equal to mx plus c model, it could be a multiple regression model, it could be a simulation model. If you want to have a reliable model, what is the accuracy requirement you should have, right? Irrespective of the type of model, you can work out. Maybe you can write 3 parameters and try to do this. Nothing stops you from doing it for all the parameters in your plant or plants. Okay. So I'm assuming that you paused this video and did that exercise and now you're back. So let's go ahead. Right. So what we have seen is basically just few simple techniques and two types of model correlations, XY type and multiple regression type. Now we are going to see two optimization techniques using Excel. The first one is single variable optimization. Instead of giving you any mathematical definition, I will show you what it is practically. Right. So let's say you have an equation of the type y equal to mx plus c, right? M and c are constants as usual. And if you go to the bottom, the question is, if the equation is of y is equal to 2x plus 5, what should be the value of x for to get a value of y as 20? Now this is very simple. It can be solved as an equation by hand. But let's say if you have to do this many times, multiple times, and automatically it can be done using Excel in few seconds. There is a function called goal seek in Excel. There will be corresponding function in other spreadsheet or simple statistical toolboxes. So here what we have done, we have written this y is equal to mx plus c equation. You see, this is y, this is m, this is x, and this is c. And in this cell G7, where it is written G7 or y, this is the formula, mx plus c. Can you see the formula bar? That is simply the y is equal to mx plus c equation in Excel. Right. Now what I want to demonstrate is what is that goal seek function. So if you see the main formula bar, there is a formula bar data, and in data there is a sub option called as what if analysis, and in that what if analysis there is another option called as goal seek. So when you press that goal seek, you get this dialog box. So you see in our equation that set cell D7. D7 is where we are calculating the value of y, y equal to mx plus c. So here we are telling Excel that set the value of this cell D7 or Y to a value of 20 by changing the value of X, right? So here we have set the value of D7 or Y to 20 by changing this cell F7, which is basically the value of X. And if you say OK, it gives you the value of X as 7.5, which is required to get a value of Y as 20, right? The reason I demonstrated is this is very simple, can be done by hand, but this is optimization, right? You have an objective, the objective is Y, the objective has a goal. In this case, the goal of optimization was a value of 20, and there are independent values which you have to change. In this case, the independent value is X, which can be changed to get the value of Y. So this is example is to show you the language of optimization, which is objective function, the value of objective, and independent variable, right? And this is very simple, but of course you can use it. I have used it few times. I don't have to use calculator so many times, right? Now the real optimization or linear programming is the multivariable optimization. Okay, so we will look at this multivariable optimization using solver functionality of Microsoft Excel. Now let me first quickly tell you that if you don't find this solver option in Microsoft Excel, the add-in called as solver is not installed in your Excel. So this is add-in from Microsoft, and installing solver add-in simply means checking one checkbox in the right place and saying OK. Please contact your IT department who can help you do that, or you can look into help and other resources of Excel and do this. We are not going to spend time on how to install solver in this training video. And now, assuming that you do have solver installed, which you can do later as well, then we will come to the typical problem which can be solved in terms of multivariable optimization using solver. Now let's look at the equation in red, which is given below. Y is equal to ax minus by plus cz plus n. Now imagine this Y is yield of a reaction, and X, Y, Z are the temperature, pressure, and level in that reactor. And obviously A, B, C, and N are the constants, right? So the problem is you want to maximize the yield of the reaction by finding out the optimal parameters of temperature, pressure, and level, right? But as it happens in the plant, you cannot change these independent variables of temperature, pressure, level by any magnitude. There is usually a limit based on safety, based on equipment limit, and so on and so forth. The fact remains that there is some limit. So let's say we are solving such a problem, and here we have to get a value of Y of 20 by changing the parameter X, Y, and Z. And the limitation, or in the language of optimization, it is called as constraint. So the constraint on X, Y, Z are like this, that X cannot be less than 2 and more than 7, and Y cannot be less than 4 and more than 8, and Z cannot be more than 11. All right. So it's like saying I want to find out the yield, when the yield could be 20, when X, Y, Z are within this range, but what is the best combination of the parameters to get the yield of 20? In the optimization, either you can set a value, or you can say how to maximize Y or how to minimize Y. These three options are there, and obviously the independent variables can be given constraints. So such type of problem can be very easily solved using the tools of the type solver of Microsoft Excel. We will see now how to do that. All right. So as usual, what we have done is we have written this equation y is equal to ax minus by plus cz plus n, and the value of y is in this cell C8, which is an equation ax minus by plus cz plus n, right? Uh, and we are also given at top the x, y, z values, which can be changed can be changed and adjusted to get the required value of y. And the constraints which are imposed on x, y, and z are written over here. Now, where to find solver? So when you go to this data main menu bar, there is an option called what if. No, next to what if there is a solver. If you have solver add-in installed, you will get an option called solver, right? So you have to press that button, and this is the solver dialog box. Now see, we have seen the goal seek dialog box. This is similar but more complex. So here also we are defining the objective. The objective variable is y, and therefore it is identified as cell C8. Now you have three options to optimize the objective, which is value of the cell C8 or value of y, which is you can either maximize or minimize or set to a particular value. In this case, we are wanting to set it to a value of 20. That's what we have written. And the next option is we have to tell which variables can be changed and which variable values can be changed, and those variable values are written in this column G, where x, y, z values are written as of now, and those will be adjusted or in other words optimized to get the value of y. But where do we tell this solver that these are the constraints on independent variables of x, y, and z, which is the next dialog, where you have to simply click add, and then you can write this expression, right? You can try this yourself. You can have a look at the help. It is simple, which basically you have to identify the cell and you have to give the constraint. I know either it has to be less than or equal to some value, or it has to be greater than or equal to some value, and so on and so forth. So we are given those constraints, and simply we have to click as solve. So the equation is, the optimization is solved, and the answer is given, which is highlighted in yellow. Y can be set to a value of 20, and these are the values of x, y, and z, which are required, x, y, and z, which are required to be set. So in other words, in this reaction you want a yield of 20, then the temperature should be 2, pressure should be 4, and the level should be 4.6. okay, that's what you get. So what we have done, if you can appreciate, if this is a reactor, without getting into thermodynamics, kinetics, we have got an equation which predicts the yield based on process parameters, and not only that, we can optimize the process parameters to find the best yield or the required yield. Got it? So that is the value of data-based modeling and optimization, at least in the simple models. So we'll go ahead now. So at this point in time, we have really covered the simple data analytic techniques, although from a process engineering point of view. But this is basically the mechanical part of how to do data analytics. So two things can be noted. One thing is obviously from here we go to the application to process engineering or wherever you want to apply these techniques. And secondly, you might have realized the value of accuracy of a model after you have seen the optimization technique, right? So if the model is not accurate, it's not going to give you the right optimal parameters to get the required result. In the last example that we have seen, if the model is not accurate, that means the yield predicted by the equation is not right, then the optimization done based on that model is also not correct. That is, it will give a combination of certain temperature pressure level, but in the plant you will not observe the desired yield. The process has not changed, the physics, chemistry, thermodynamic, kinetics has not changed, only you have used the wrong model, right? So accuracy is the main factor in applying data analytics in process engineering problems. That is what we have to keep in mind. Right. So whatever models we have seen, y equal to mx plus c, or multivariable model, or the optimization using solver, these are all simple models, right? Simple models and simple optimization techniques. But the advantage is they are very useful in day-to-day work, and they are also very quick to build. And thirdly, you don't really need any thermodynamic, kinetic, and so on and so forth parameters. Lab data and plant data is sufficient to do most of the modeling, right? Of course, in this world there exist complex models and complex optimizers, the kind like a model of a complete plant. It could be a steady state model, stoichiometric model, or it could be a database model, it could be a hybrid model. Yes, there are people who are building complex models. In fact, we do at Benchmark, we build complex models, right? Building complex models is out of scope of this introductory training program. So what we have seen is the elementary models. Of course, we'll provide you some introduction to the complex models and complex optimizers. And in real world, whoever is making good, accurate, complex models or optimizers, there is a large amount of component of art involved in addition to the science and mathematics till today, right? In other words, there is no tool available in market today where you just feed a ton of data from plant and click a button and get an accurate model of the whole plant. And by plant, I mean an ammonia plant, or a crude distillation plant in a refinery, or perhaps a petrochemical plant, let's say a naphtha cracker or something like that. So there is no tool available, no software available where you just put a ton of data from plant and lab and you get an accurate plant model, which is plant-wide model, coming out of it. If you do get some vendor who says I'm selling it, just go and grab it, whatever is the price, right? There is no such tool available till today. Okay, let's go ahead. So having done the review of the techniques, now we'll go to the application part, and let us recall how we defined application. Application basically means you have a problem, you have a process engineering situation in front of you, and if you want to apply data analytics, you are basically defining the problem in such a way that it can be solved using data analytical techniques, that data analytic techniques like which are enumerated above. Okay, and then of course building a model and solving it, right? So we'll go ahead. At this point in time, we can also define AI as in process industry. Some people call these techniques and some of such activities as AI. AI means artificial intelligence, but to my mind, the usefulness of these techniques is as good as the creativity and the intelligence and the imagination of the person employing these techniques, right? So it's really the person's intelligence which is playing out here, and you will see when we do some examples of application of data analytics. But of course, the mechanical process of building a model from data is of course artificial intelligence. the software is crunching the data and getting a model out of it and telling you how good the model is. Of course, that is AI. But anyway, we are not here to define, we are here to do a process engineer's job. So let's go ahead. We will see one examples one by one, but most of these examples are from plant operation, process monitoring, continuous improvement, decision making, performance benchmarking. We'll go one by one, right? Now, this is a popular example in continuous process industry, a calculation of a stream property. As we talked some time back, for any plant which is operating continuously, there is always a laboratory in the same premises. The operators take out sample maybe once in a shift or once in a day, and those samples are analyzed basically to know what is the composition of various streams, either the products or the raw materials or the intermediate streams, right? And although people have all kinds of simulators and various tools, these properties are not calculated reliably. People have to depend on the laboratory. So in this situation, the data analytic techniques are very useful. A lot of people, including myself, have developed a lot of good correlations using data analytics to predict stream properties very accurately. So the generic problem is like this. Let's say there is a reactor, and the stream outlet of the reactor, the concentration of a particular species or a particular chemical is to be found out. Right? So A and B are the reactors, and there is an outlet which has product, and we have to find out the reactor outlet concentration, right? And the typical reactor operating parameters are temperature, pressure level, and the inlet concentration of A and inlet concentration of B. So by now you would have realized if these are the parameters and if data is available, it is absolutely easy to fit an equation, right? About in a 1 minute to get a correlation and know how good that correlation is, and we can always run that correlation and find out how accurate it is as well, right? So basically you have a data which is the reactor outlet concentration as received from lab report, and the corresponding time, temperature, pressure level, and initial concentrations of A and B. That's the data you have. And then we have to just fit an equation of the type, reactor outlet concentration perhaps is 100 into temperature plus 200 into pressure minus 0.5 into level plus 1 into concentration of A plus 2 into concentration of B plus some constant, something like that. Okay, that will be a linear equation to find out the reactor outlet concentration, right? You can do this instantaneously. It is just one calculation, and not only that, a lot of people are using this to put it as a calculation tag in the control system or DCS, so that this outlet concentration, calculated reactor outlet concentration, is displayed just like a tag, temperature or pressure, which is quite helpful to the operators and engineers working in that plant. So this is one very good example of application of data analytics. So the situation is, with current level of with the current available tools of simulation and other calculation, as well as whatever calculation methods we have learned, it's not possible to predict or calculate the reactor outlet concentration uh, with good accuracy or with good confidence, and we have to take help of lab, right? But if you have a good correlation, we are defining the problem or we are applying data analytics as saying, can this property of reactor outlet concentration be predicted using a correlation of process parameters? Answer is yes, and then it can be done with the right amount of data, the right parameters. Okay, so this is one application. Now, typically, you might have come across in operating plants a problem like this, that one heat exchanger has punctured. Let's say shell and tube heat exchanger has punctured. Now, immediately you cannot buy and put it there, but there is one heat exchanger lying in the yard, which is in good shape. It is the same geometry as the current heat exchanger, but it has 20% less area. Will it work? And will it work? It means, will it do the job of that heat exchanger or the normal variation of throughput and properties of feed, or you will have to reduce the throughput of the plant, which is loss. That is the usual problem we have, and sometimes we engage consultants to get a confirmation. But here is a way it can be done using data analytics. So basically, we want to find out the heat duty of the heat exchanger, maximum heat duty, and that heat duty depends on the area as well as the heat transfer coefficient. Now, this heat transfer coefficient, either it has to be calculated, which we think is a expert's job, or we have to do using a lot of thermochemical data. Now, if you want to convert it into data analytics solvable problem, we can say, hey, can this heat transfer coefficient be correlated with the parameters that affect this heat transfer coefficient? Of course, from our concepts, we know Reynolds number, Prandtl number, these affect the heat transfer coefficient, and these are the individual variables, diameter, velocity, density, viscosity, heat capacity, heat conductivity. All these parameters, they affect the heat transfer coefficient, right? Now, if you have a large amount of data of the old heat exchanger which got punctured, you can correlate this data to get the heat transfer coefficient correlation with all these variables. And from the geometry of the new heat exchanger, simply use that equation to find the heat transfer coefficient of the new heat exchanger. Obviously, the diameter of tube may or may not be same. Definitely the fluid velocity U will be different. Density, all these physical properties can remain same. So basically, you can get the new heat transfer coefficient for the same duty in the new heat exchanger, which has 20% less area, with good amount of confidence, and then you can compare whether it is good enough for the duty which is required, whether that area is good enough for the heat transfer, right? So the situation which can be translated into a data analytic type of problem and then solving it, it is possible. Another area is for batch processes. As very few of you might have used these techniques in batch processes. The batch processes are typical. I have worked in batch process plants for about 3 years, so I know. They have short campaigns where the plant produces a product for maybe 6 months or a year, sometimes much more than that, but campaigns are usual. So you don't really have a lot of time to develop process and so much of data and information about the process. And all these techniques like APC and some of the simulation, etc., is not widely used in this space because of all these constraints. So interestingly, these data analytics techniques could help a lot in batch industries. Now, the most important, we are talking about operation of the batch processes, right? Of course, it can be used for design scale up as well. You can contact me separately if you're interested to know about it. We will not talk about because it will take the direction in a very, it will take the discussion in a very different direction. So basically in the batch process you have a reactor and it is operated in a batch fashion. That is, you first take few reactants, maybe heat those, then maybe add some more reactants, heat, cool, and then the batch ends, and the typical objective is some concentration at the end of operating period, operation of the batch. If it is the reactant, then the reactant concentration has to go to very small level, let's say less than 1%, that is considered as the end of the successful batch. So that is the typical batch operation. And so how it is done typically. So the batch is run on the basis of a standard operating procedure, and the sample is taken at the end, and if let's say the concentration is more than 1, then again either some reactant is added or some temperature is maintained for some more time, and then again sample is taken, and once the concentration of the reactant has gone down below say 1% or whatever is the limit, then the batch ends and then it is cooled and transferred. Now same problem can be converted into a problem defined in a way so that it can be solved using data analytical techniques, right? So what we are saying is our goal is to know the concentration of reactant at the end of batch, right? The end of SOP period. And we know from our concept that this concentration is a product of the temperature profile. You know, what was the temperature of the batch during the batch time, the initial concentration of reactants, and the addition of various reactions, the amount and the rate at which the reactants were added, right? And let's say the steps of reaction are like these: you charge the chemicals, then you heat, then you start addition of other reactants, then maintain a temperature for some time, then again raise the temperature in couple of hours, then maintain for 4 hours, and then sample, right? Now you just cannot have one temperature, because being a batch there are multiple temperature, which is temperature at the start. Let's say what will be the parameters affecting the concentration at the end of batch. You know, what is the temperature at start of the batch of various reactants, what is the temperature after 1 hour, what was the temperature at addition was done, what is the temperature to which the temperature was raised after 2 hours, and what is the temperature at which the temperature was maintained, right? Then initial concentration of reactants, then what was the average addition rate of reactants, you know, if there were 2 reactants, what was the rate of addition. All this data can be obtained, and this data can be obtained for a number of batches, right? Let's say 100 batch, 120 batches, and we will have a data like this. So for batch number 1 to 120 we have the final result, the limiting reactant concentration at the end of batch, 0.5%, 0.7%, 2.1%, 1.1, so on and so forth. You might have seen results like that, right? And this is the charging temperature, 35, 36, maybe so much of variation, addition temperature, what was the temperature after raising temperature, what was the temperature for maintaining the temperature, right? What were the initial concentration of A, B, C in that batch, and what were the addition rates of reagent M and N, average addition rates. And there will be a data of so many batches, and then it's so easy to fit an equation. Of course, you have to see how good that equation is and how accurate that prediction is. That need not be said every time. And based upon the confidence we get that this is a very usable model or a usable equation, you can save a lot of time waiting for lab result. You can simply do corrective actions using this equation and perhaps later confirming with lab, or you can end the batch if the equation gives you a very confident prediction that the the reactant temperature has gone down 1%, right? So in batch process, in addition to quality, yields, time is very important because it's a batch process and there are batch schedules, and the plant throughput itself depends upon batch time. And if you are able to save batch time, your throughput goes up. That's the benefit one can get out of it, right? So we have talked about this. Okay, here is another example, not from process engineering, but this news item maybe a week ago caught my attention. It was in one of the dailies, Daily Hindu, and this is basically about a model, a data-based model, of course using some scientific concepts, which is done to predict the rate at which the birds flap their wings, the frequency of flapping their wings, and that's a simple linear model, as you can see. Um, Let me make it bigger so that you can appreciate it, right? So as you can see on the x-axis, there is some bird's physical property in terms of mass and wing area, and then there is a wing beat frequency on the y-axis, and apparently there is a good linear correlation they have got. So imagine you can predict what will be the wing beat frequency of a bird that you may not have actually seen as well. So if we can do this, imagine what knowledge we can generate about our plant, our process, our people, our customers, you name it. So although this is not a process engineering related example, I thought I will just take few seconds to mention this. Now at this point in time, let me summarize the approach of data analytics. The data analytics techniques per se, the mechanical part is well understood. So what we are talking about is how to utilize, how to apply these techniques. So basically we need practice, and the practice is not for building a model, but the practice is to visualize, how to visualize the system in terms of parameters, and the basic concepts, our basic process concepts, and then how to define a problem which will make it solvable by data based models, right? That's the algorithm, there is nothing else, and it's only practice which will make you comfortable deploying this approach, right? Let's go ahead, we have a few more things to cover. So to summarize, we have to imagine a system in terms of parameters, and these are basically operating plants, so it is easy to visualize that in terms of measured parameters and lab analyzed parameters, and perhaps properties of the feed and products. And then we can build these parameters, and we can build these models, and these models can be used for any work that is done by process engineers for analyzing, plant corrections, checking performance of equipment or plant. That's it. Fortunately, this practice is all mental practice, so it doesn't require any money definitely, and not much appreciable time, right? You can do it while traveling from point A to point B when you are not driving, that is, okay? Just an example. Okay, now here is an interesting application of data analytics to detect abnormalities in the plant, and these abnormalities, if they are detected early, we can actually avoid the consequence of these abnormalities, which is usually an accident or a equipment failure or a process upset, right? Now the basic concept of detecting any abnormality is explained by this example. So let's say, as usual, there is a parameter which has a range from 80 to 120. Let's say this is a temperature, and let's say the temperature should be 82, which is towards the lower end of range, depending upon the process parameters, feed parameters that time. But if let's say it is on the higher end of the range, let's say 118, that's a big gap, between expected and actual temperature, right? And therefore, this temperature can be flagged as abnormal. Okay, so to detect abnormal, this is one part. And as you might have guessed very rightly at this point in time, the expected temperature can be obtained from a model, right? And that model has to be accurate. And the actual temperature is, of course, the measurement in the plant, right? And now if you see how an accident, breakdown, or any abnormal event happens, let's see the same temperature in a longer time zone. So the bottom is the range, okay? And how the accident happens, let's say this temperature start rising from the bottom end of the range, and then it goes out of the range and much higher, and that's where when the event occurs, let it be accident, breakdown, process upset, anything. Now the time from the temperature rise started up to the point where the temperature went out of the range, that's the time when the event could have been avoided. Now, normally what happens, this is the time when all the time the temperature is thought to be within the range, and therefore this temperature is not given the tag of abnormal, right? So if we know the tag of abnormal, this temperature is behaving abnormally, and we can also observe the trend that it is rising. So anybody can understand that here is a temperature which is abnormal and which is going rising rapidly, and perhaps it will go out of range after some time, and then it will cause some physical event, right? So everybody sees this trend, but nobody thinks this will go out of range because they don't think anything is abnormal. So what we are doing with our data analytical skills, modeling skills, and whatever, we are trying to examine which of the parameters is abnormal, right? Of course, the reason for abnormality could be really abnormal process behavior, or it could be simply a bad measurement. But thing is, out of the hundreds of important parameters, we have to point out what is abnormal, right? And once we know what is abnormal, we can rule out the abnormalities for the identified tags and really focus on something if there is in fact something abnormal. So that is the basic concept in finding out abnormality in the plant and avoiding events of breakdown, equipment failure, process upset, or any such undesirable events by detecting the abnormalities early and doing corrective action. Again, at the cost of repetition, let me tell you the importance of accuracy of a model. Such abnormality can be detected only if you have a great confidence or a low error on your model which you are using for detecting the abnormality. And this we have talked about, what is accuracy and how to look into it. We have also seen this, that the error should not be more than 1/10 of the range, or accuracy has to be minimum 1/10 of the range, right? Now, typically we do this exercise, what are the parameters which can possibly indicate abnormalities in your process. There are some key parameters, and then we write the accuracy requirement, etc. So you can do that exercise now or at any comfortable time. You can just make a note that you should do this exercise so that this concept sticks to your thinking. Now, again, our conventional approach of doing any analysis calculation is, material balance, energy balance, mathematical modeling, simulation, in short, very rigorous type of calculations. And the alternate approach, this data analytics approach, is defining the same problem or the same situation in such a way so that we can solve the question using data analytical technique of developing simple models and then doing analysis or optimization based on those models. Now, at this point in time, I don't want to tell you what work you are doing, but just as a summary, there are so many activities, calculations which you are doing. Of course, these will be different depending upon the type of industry which you are into, but basically the common activities are plant operations, having basic knowledge of process, plant, SOPs, the control systems and various data systems. Then the unusual operations of emergency, startup, shutdown, day-to-day process monitoring, and then of course various other things like catalyst monitoring, equipment monitoring, then of course making various reports, giving data, and so on and so forth. Now everywhere this will be different for each individual engineer, so one should try to think creatively and apply data analytics wherever possible, right? So in summary, the whole game is build models from data in few minutes and use these models for getting results, right? And it's okay to deliver results using simple ways, even if we are engineers. We don't have to create a monster of a problem and then tell everyone what great problem we are required to solve and then solve it in few months' time. We can deliver the same result perhaps very quickly. Now, we also have to think that the world is going to use these data analytic techniques going forward, and a lot of people are already using it. But what happens when these simple methods are not utilized? So the engineers and particularly process engineers in plants have two options, Imagine a situation, very typical situation, when the operator says, uh, we got the lab results and the lab says the quality is bad, so I know directionally we have to increase the reflux, and you are my engineer, please tell me how much reflux should I increase. Now of course the engineer can do all sort of rigorous and calculations and spend few hours, do some simulation, and give a very quantified answer like increase the reflux by 2.3%, right? But most of the times the engineers will not have that much time or resources to do such rigorous calculations, and the engineer may say, okay, increase the reflux thoda sa. Thoda sa is a Hindi word. It just means, increase the reflux a little, and then let's check the next lab sample. Perfect. This can be done. It's a practical way of doing it, but then all you lose is the time to do correction in the process. That's the profit you are losing. Okay. But imagine if the engineer had a simple chart like this where quality versus reflux ratio is plotted and a very good very good correlation is available which can accurately advise the correction in the reflux. So the same 2.3%, maybe with some degree of inaccuracy, could be told to the operator then and there. right? Now, those were the direct application of data analytics into process situations and process analysis. Now, this is a decision-making framework. We have talked about this in the session for owners, initial session. I don't know whether uh, the ones who are watching this session have listened to the earlier discussion. So quickly, this is a framework which has been successfully applied in many industrial situations, many decision-making situations, many evaluation situations, and the same thing can be used for technical decision-making. So what we are doing typically in decision-making, we are working out alternative options to solve a problem, and then we are evaluating the options. The alternative 1, alternative 2, alternative 3, alternative n. So sometimes you are too focused on the technical objective, like what is the best heat transfer rate or something like that. But it is better to have a broader framework of decision making, even if it is a technical problem. Generically, these are the 6 parameters: effectiveness, usability, maintainability, life cycle cost, which is about 10 years, and the risk, and as well as the company time or additional headcount required to solve the problem. Now, let's say you are talking about some alternative projects. Perhaps there is an energy saving project and there are a couple of alternatives. So here the effectiveness, if it is a if it is an energy conservation project, the effectiveness is whether energy is definitely saved or not, right? And if these are physical parameters, physical equipment, some data is available, some correlations are available from the vendor, definitely how much energy can be saved in your plant can easily be worked out using data analytics techniques. You don't have to do the whole plant simulation, and the alternatives can be compared on that. Now, this usability, maintainability is usually visualization how these systems will be used and maintained, whether at all they are usable and maintainable. And life cycle cost is usually a simple arithmetic calculation of one-time cost and recurring cost and finance, interest rates, etc. The data analytics can definitely use to quantify risks in the decisions, if any. And finally, whether any additional headcount is required, not for the project, but for the actual usual day-to-day operation and maintenance of the system, that has to be seen. It is not exactly data analysis, but visualization. But if we have this broader framework, then many times our perception of what is the right alternative for the plant problem changes. Instead of just focusing, I want to reduce energy at minimum cost. So alternative 1 saves 100 energy, alternative 2 saves 90 energy, and the cost of energy 1 is also less. But perhaps it may not be the best alternative on if you compare on all these parameters, right? So this framework is one thing, and another is you can freely apply data analytics wherever you want to quantify, especially the difficult things like effectiveness or risk, okay, which are related to the performance of such new equipment in your own plant. Okay. Going forward, the same digital techniques can be used for continuous improvement purpose in process industry. This topic is just mentioned here because it needs few simple process related topics which are covered in next session, of performance benchmarking. So we will cover this small topic of continuous improvement there. Now we have been talking of data analytics, and remember what we told in the beginning. The data analytics needs three things. One is the data analytic techniques, which we have seen for quite some time now, and how to apply creativity. The second thing is domain knowledge, which is again related to creativity of defining and solving the problem. And third thing is the data itself. Now let's talk about data for some time, because that is the basis of all these activities. So we will talk about data sources. We'll talk about how to clean or how to process the raw data so that it can be used to make meaningful models and do meaningful analysis. So there are many sources of data these days. This chart is having bit small font, so I'll read out on the column on the left. Various data sources are mentioned, like process data in control system, process data in real-time database system. And then there is a question whether snapshots are available. I will come to you about snapshots. Then laboratory data is there, events in the control system and in the real-time database. Events are also stored, right? And then there is instructions data. These are typically the instruction given by engineer to the operators and technicians. And then various logs are there, various plans, production plans are there, various reports are there. All these are sources of data. This is not something new. You already know, you already perhaps use all these in day-to-day work. Snapshot is a concept in data, in process data particularly. If you see the data in your DCS or in the real-time database, there are options of data. You can have a hourly average data, you can have a 5-minute average data. Similarly, there is an option called as snapshot data. Now what is a snapshot? Now snapshot means it is the exact raw value at a particular point in time, right? So when you have, say, TI 101, temperature indicator 101, and if the hourly average is 100, okay, that means from, say, morning 10 o'clock to morning 11 o'clock, the average temperature was 100 degrees Celsius. But if you want to know the snapshot of TI 101 at 10 o'clock in the morning, it could be 105. What is the exact temperature at that point in time. Now for data analytics, we need snapshot values. Please note this. We cannot take hourly average, we cannot take day average, we cannot take week average. We need data in its most granular form with respect to time, which is snapshot. Okay. And knowing all these different parameters, you can mentally think about the things written in the row above. What are the names of the systems? For example, control system, you may have some control system, ABB, Yokogawa, Honeywell. Then real-time database, write the name. If you don't even know the name of the system, probably you need to check with your instrumentation or IT guys and get familiarized with that. Okay. And then you have to note what kind of data is available for how much duration. For typically the control systems, especially the older control systems, keep data only for a week or so. Real-time database system can store for years together, but many times the old year data is available in archives. Then granularity of the data, we talk of snapshot. Now some systems do not keep snapshot, they keep only hourly averages, something like that. So you have to know what is the granularity of the data which is available. Then in old times it was important to know whether the data is electronic or paper, because if it is paper, then somebody has to type it. It is a separate project activity chargeable to third party. But these days most data is available in electronic format. And right, and that's how we have to know what are the sources of data, what is the granularity of the data, what is the duration of data available with us. And it is good to keep this map updated with you, because you never know which problem in which area you are going to solve. Now, having known what are the sources of data and probably having the data in front of you in your computer, then what you will see is raw data. Now that data, let's say this is temperature, pressure, plant data. So many times there will be signs like this, number 1, not a number 9, or some characters. These are basically bad data. The bad data could be bad numbers also, grossly inaccurate. If the temperature is usually 100 plus minus 20, but if it is showing 3000, it is of course bad data with respect to the range. Again, we have discussed this. We have to know the normal range of a parameter, and we have talked about how to find the range. And once you have the raw data, first you have to remove the data which doesn't make sense, which is something that's non-numbers, some gross errors which are grossly wrong, right? And if you want to be extra careful, you can remove all data which is plus minus 2 standard deviations above or below the average. Okay, average plus 2 standard deviation is the upper limit. Average minus 2 standard deviation is the lower limit, and whatever data is there outside of this limit can be removed. If we are having a lot of data and you cannot look into each parameter, find out its range, then this is a bulk data cleaning which you can follow, and it is useful in many cases. Remember, you have to take snapshot data. Okay. Now when you take a plant data, you will have two types of data. One is a continuously available data like temperature, pressure at very good frequency, and there is non-continuous data like lab data, which is available maybe once in a shift, once in a day, or once in a week maybe. So when you want to have a complete snapshot of data in a plant, let's say your lab results are available every day at 7 o'clock in the morning. Then the only way you can have a snapshot is 7 o'clock in the morning every day, where you know the lab values, the temperature values, the pressure values, and so on and so forth. Now let's say you have only one set of data in a day, then how much data is enough to do modeling, or at least to do some meaningful calculation with the data? So just remember the number, you need about 50 data points to have some statistically confident analysis or conclusion making out of that data. I'm not talking about a model, because model we have already talked about. The model is not just about the amount of data. It has to cover all modes of operation, let's say 2 years, where all modes of operation, all variations in operations are covered. And from that data, if you're taking perfect random numbers, then yes, you can have 50. But again, you have to have lab and process data together. So again, if you take 2 years of data, and let's say you have lab analysis only once per day, it's only about 700 points. And half the days they don't do a lab analysis. So you will end up with say 350, 400 data points, right? And minimum required is 50. Okay. So when you choose random, you can choose 50, but you can also take all 400, it's not going to increase calculation load. But in fact, you will have better models, right? But for normal analysis, if you want to draw conclusion, what is the average range of a parameter, you can have 50 data points to reduce the workload. Okay, so that's about raw data, how to clean it, how much is required. We have talked about this, right? So now we have certain topics which are benchmarking of non-manufacturing process, some procurement guidelines, some project guidelines. So these are not necessarily related to process engineers only. These are in fact related to excuse me, engineers other than process engineers, and process engineers could also be involved in these activities. Now in the next session we are having some more detailed discussion on process benchmarking. Now this is the same technique can be applied for any non-process or even service process, right? Um the trick remains same. Even if it is a process, let's say service process, you have to define in terms of parameters, define its objectives, constraints, right? And there is a procedure followed to benchmark it, right? Let's take an example to make it clear. Now let's say there is a maintenance engineer, and the task that he is doing is to find out, analyze the delays which happen in various maintenance job orders, and find out whether any system improvement can be done so that the delays can be saved across every job, right? So now one thing of course is to know the maintenance process. We are not going to cover it here. We are simplifying it, and we are applying our data analytic approach, that is parameterize the process, right? So the objective here is delay, right? So delay is measured in hours, right? So in a job order somebody is writing delay, and there are three reasons why delays have happened and what is the approximate allocation of this reason for the delay, right? For example, in job number 1 there was a delay of 10 hours, and the one who filled up the log sheet said 10% of delay was due to non-availability of people, 20% delay was due to locating spares or getting spares, and 70% delay was due to finding tools or related tools. And of course they have a lot number of job orders, maybe 150, for which they have meticulously applied their judgment and filled up this data as and when the job was completed. Now once we have this, uh, we will define the process in terms of objective and constraints, right? Remember we used the same terminology when we looked at the multivariable optimization, right? So these are the same equations shown in a graphic format. So let's say this delay is the objective and minimizing the delay, that is the goal, okay? And if you take all this data and sort it on delay, uh, you will find such a graph, which simply means a delay is caused due to various these three parameters, and these three parameters have a relationship with delay, which is a linear relationship. Perhaps there exists an equation, right? And when we talk of constraints, that means the tools, in the middle there are average values. Average delay was, let's say, 10 hours or 5 hours or whatever it is. The average delay due to spares was so many hours, the average delay due to people was so many hours, and average delay due to tools was so many hours. Okay, and there is a practical limit below which you can either increase or decrease the delay due to any of these reasons. Just like process, this is also a maintenance process, and there will be some logic to define this limit. We are not getting into what is the logic in deciding these limits, but we just recognize the fact that every parameter will have some limit, right? In this process, what we are going to do is we are going to find what constraint is limiting the delay reduction. Now in this case you can visually see that the tools is the limiting constraint, it cannot be reduced to a great extent, and its impact on delay is also quite flat. Even if you reduce the delay due to tools, the delay is not going to come down significantly, right? But that's the delay which you can reduce. That also means there is spare capacity in terms of spares and people. There is no immediate constraint on these parameters. And all we need to know now is how much this delay due to tools can be reduced, right? So let us just expand this diagram, or make it a little bit more readable. And this is the same diagram, and the logic is like this. If the process is adjusted in such a way, the work process, the way people work and attend to job orders is changed in such a way that the delay in locating tools is reduced. So basically, if you look at the tools, this is in green, and there is a vertical line which says this is the average value of delay due to tools. So when we say the process is changed in such a manner that the delay due to tools is reduced, that means this average is going to go on the left hand side, right? And as you see the thick green lines, there are the limits on the tools delay. So if you are going to reduce the tools delay, the average is going to shift towards the left, towards the lower limit of this parameter, right? And therefore correspondingly, since this parameter tools delay is related to the total delay of the job order, the delay total delay will also reduce by an amount, and that can also be seen as shifting of the average delay towards the lower limit, right? So this is what is the concept. Now it is possible to quantify how much this delay in tools can be reduced. And as a thumb rule, just understand that for any constraint, these reduction, or the movement of this average value in the desired direction. In this case, we want to reduce it. In some case, you may want to increase it. But the magnitude of this average shift is 1/3 of this range between the average and the limit, right? And if you recall, this is 3 standard deviations. So basically, roughly 0.8 to 1 standard deviation is the magnitude of the average shift of the constraint. And then all we need to do is to relate this change in average of the tools to the change in average value of delay, or in simpler words, if this parameter is changed, what will be the corresponding value of the other parameter, which is simply the XY plot which we have seen at the beginning of this session, right? So let's say numerically this average value of delay due to tools is there, and let's say the lower limit is about 30% of the average. So 1/3 of that distance is 10%. So let's say the possibility to reduce delay due to tools is 10%, and let's say the corresponding reduction in the total delay in job order is 2%. Okay, so that's how on an average basis for this maintenance process, the physical description is like this, that there is a maintenance process, there is a maintenance practice, there is a way how people do maintenance in this company. But somebody applies his mind and says, I'll focus on reducing the time spent in locating or getting tools for a job order. And if he's successful, how much time can be reduced in finding tools? So we have found it out. And then this reduction in time of finding tools is related with the delay in the particular job order. And if you do this, and since these are average values, these are the average values for the maintenance process. So one can say that I have reduced the average delay by 2% in my whole of maintenance process, and that of course is by reducing delay particularly in locating tools. Right, so many will have a question in mind, how can we say that any constraint in any plant, in any process can be improved by a particular magnitude. So this slide tries to explain the logic behind it. This is actually based on a paper in hydrocarbon processing. The reference is written at the bottom of this slide. There are many papers written on similar lines, but this remains to be the oldest and paper which explains the concept in a very nice way. Of course, a bit heavy statistically, but I encourage for everyone to go and read this paper. Now, the basic concept is like this. So, by the way, this paper was written from a perspective of how these variables can change due to good control or APC. Okay, but the concept remains same in any optimization. So, this is the chart of the variable. Let's say this is the chart of the delay due to tools that we are talking about. Now, obviously, this chart or the data will have some average and some standard deviation, which you can see as a lower and upper limit of the data variation. Now, this the explanation given in this paper states that any variable, if the process is optimized, what is the effect on the limiting constraint, and the limiting constraint average value changes. That is the basic effect, right? In our example, the delay due to tools, it can increase or decrease. That's the meaning of average increase or decrease. And in this case, we are interested in knowing what is the decrease possible. So the change in average value of this parameter in any direction, any profitable direction, either above or below, is quantified. There are many correlations given, but the one which is applicable in almost all cases is this, that the move in average possible in the profitable direction is 1.65 into standard deviation divided by 2. That is, if this is the chart of delay due to tools, the change in average value of this delay can be calculated by this function. You take the standard deviation value, multiply it by 1.65 and divide by 2. So this is roughly 0.8, or as a rule of thumb about 1 standard deviation. That means any constraint in any process, if the process is optimized, can be moved by an order of magnitude roughly 1 standard deviation in the profitable direction, above or below the average, right? So once we know the change in constraint value possible, then what remains is actually correlating this change in the average value of constraint to the change in average value of the objective. Now that's a matter of finding out how much will be the change in objective function for a corresponding change in constraint. And obviously these two variables, the constraint and the objective function, are very correlated, and if you plot a XY plot, you will get a good correlation or a good line, as you can see. And it is very easy to find out for a given change in X, which is the constraint, what is the corresponding change in Y, which is the objective. All right, and that's what our goal is, which can be very easily achieved. Then we have two topics on project execution and procurement. So in project execution, The digital project will have typically the steps. One is the business case, assuming that it's a new digital technology that you are getting into. So typically there will be a business case, and whether this is the infrastructure type or a decision making type, what is the expected benefit out of it, money benefit as well as business process efficiency, business process improvement, ease of business process doing. And then we have a framework. You remember the framework, 6 parameter framework: effectiveness to risk and headcount. You complete as much as possible at the business case level when very little information is available. And then of course there is a specification based on the success factor framework, what we have talked about. And then usually an external party is contracted who develops a detailed functional design based on their own technology. And then the data is collected, models are built, and then the models are demonstrated and accepted. Now you know what are the basic factors to look at the model's accuracy, usability, etc. And then once the system is in place, the benefits are verified. We have already talked about how to verify benefits on account of accuracy and actual better decisions made. And the success of digital system doesn't is not accomplished the moment project gets commissioned. Rather, it starts there, because the benefits are available once the commissioning is over, and those benefits have to be ensured over the life cycle of the digital project. Right now, the digital components are well known. You have hardware, software, services, training, AMC. These are also the components in most of any engineering project. But from the point of view of digital solutions, it is it's a good practice to put the hardware as well into the supplier scope. That is where the hardware design and hardware architecture, etc., is critical in executing this system. And of course, you have to give your IT policy to the vendor so that they can design it properly. And the main objective is to ensure feasibility of operation of the system. Because if there is not much of liability on the vendor to make sure that the hardware is compatible with their solution, there could be issues during commissioning the actual system. But of course, the times are changing. A lot of software vendors, they say our software is well tested and we don't really want to get into hardware and maintaining hardware. It is better to go with your umbrella hardware agreement with your established hardware supplier. So it depends upon situation. The deciding factor is having enough skin of the vendor in the game, so that they give all proper inputs to ensure that their system works on the recommended hardware. Software, apart from the technical architecture and the IT policy and so on and so forth on software, one important aspect is the license agreement, which has a lot of impact on usability, cost, and upgrades. We have some detailed discussion on the next slide. Then again, in any digital project, you should put all services in scope of the vendor. Now, the vendor has to think of all services needed, and the vendor has to call out if some service has to be done by the customer, right? So from your side, you have to put it there, because you can imagine implementing the system which you are evaluating, but perhaps the vendor can imagine it a lot better and call out your role much better way, and they can estimate their role in a much better way. Then training is very important in both infrastructure and decision making type projects, particularly the user training. And there is usually maintenance and engineering training as well. Instead of trying to get expert in that software, it probably the focus should be to know in and out of various maintenance and engineering activities, how we can visualize those activities so that you can interact with the vendor at a later date, knowing what the story at the vendor side as well. Um, okay, and then of course the AMC is very important part. Apart from the services which should have all modification in the scope, the software AMC should be worded properly. Typically the words used are software updates, these are bug fixing patches, right? But apart from that, all version upgrades should also be in scope of the AMC. Some version 1 is there, now some new version 2 has come up, that should also be supplied as a scope of AMC. And then there should be clear terms on emergency support, remote support as well, right? And if the system is big enough, there should be some service levels on resolution time, duration, etc. Because answering AMC call is a small item for a vendor, but it has a potential of causing a lot of damage at the customer end. So even if the vendor is going to charge extra, it's okay to pay extra and get these services, and it should be documented on what basis this service should be billed. Now, on the software licensing front, there are few items which have to be clear, and basically your understanding about those terms has to be clear. The term of the software is very important. Whether the software you are buying, can it be used forever, or it has a time lock? It can be used for a year or 2 year or 5 year. That is important to know that. Then there are user limitations. The typically if the software is a server based software or a cloud based software, then usually there could be limitation on how many users can use the software concurrently at a given time. Okay, so it has to be clear how many users can use the software concurrently or at the same time. Excuse me. Then you have the agreement should have some description of software functionality in English language. It could be a set of brochures as well, but there should be some description of the software functionality. Then some license agreements restrict the geographic use. Let's say you are having the software on your server, but you cannot use it beyond, let's say, the geography of that town, right? You cannot access it from another city where your own office is there. Such restrictions, if there are any, have to be clearly mentioned in the software license agreement. That is also very important from evaluating competitive products as well. Limitation on number of concurrent users we have talked about, and usually there are some hardware and software locks. So we have to know very clearly how these softwares are locked, whether they are locked to a computer, they are locked to a server, or there are hardware locks or dongles. That has to be very clearly mentioned in the license agreement or whatever is your base contract document. Another commercial aspect is delivery of the software. In many countries, the software is taxed differently. Um, if the software is delivered as a server download, there is a different tax. If the software is delivered on media, that is USB or a CD, it is taxed differently. And custom built software is also taxed separately. So one has to be very clear on this aspect, how the physical transaction is going to happen, and therefore what will be the tax implication. We have talked about this software support in AMC, annual maintenance contract. So the AMC has to have software support as well. That is the remote support typically available, but if there are really any bugs and defects, who is responsible for that, who will pay for that, and if there has to be some service agreements, right? So if you have bought the software for 10 years and if somebody takes 10 years to fix a defect, basically you have lost all the opportunity. So some level of service agreement apart from the project services could be there in software support as per the industry and the technology setup. And then important part in terms of contract is the liability, because the softwares do have various intellectual property angles, which being a user you are not really concerned, because what you are buying is a license to use the software. The property remains of the software vendor, and therefore all the liability should be defined to the vendor, the software vendor. And if you are taking any liability, you have to be very clear what liability you are taking and what is the quantity of the liability which you are accepting. Another aspect is cancellation. Software orders, a lot of people think that if they don't want to use, they can simply terminate the order. Many cases the contracts don't allow that. So it is extremely important to be very clear in the agreement about what is the term on cancellation, right? So if it's a software for which you have to pay periodically, and if you don't want to use the software for your own convenience, can you just terminate the contract? Uh, that has to be very clear, and what will be the commercial implication for that. Then of course there are performance guarantees in some cases which are like service level agreements. uh, you know you are buying the software to do a particular task, but if the software doesn't do the task, then how to handle it commercially as well as from a project perspective, that clarity should be there. And finally, commercial part, all the known and foreseeable costs like software usage fees, the update fees, the upgrade fees, whatever fees there are there should be counted and agreed upon for the complete life cycle of the project. So these are some generic pointers. Every project is different, but these are the major aspects, right? So at this point in time, we have really covered almost all the topics which are necessary at an introductory level on digital systems, as well as applying data analytic techniques in process industry. Now there are two topics which are more focused for the process engineers. One is a more detailed description of the performance benchmarking for chemical plants, and second is plant operations optimization and some introduction to the complex models. So we will start with that. Okay, so we get started with performance benchmarking for process plants or process equipment. Remember, generically, we have covered very briefly the same technique in the maintenance example. Now, obviously, process plants are a bit more complex and we need further more concepts and further more work to be done. Further, if you are talking about plant performance benchmarking, a lot of experienced people will question what you are talking about and you have to defend it. So in this section, which is primarily addressed to the process engineers, of course others can also watch it, it's not particularly difficult, but we are going to talk about qualitative and quantitative performance benchmarking, but mainly the quantitative, that is the subject matter of this training. And then we will talk about how to do the benchmarking. Many times the objective itself is not well defined. Then one has to discuss with the concerned plant and management people and come to an objective. Then we of course see the detailed performance benchmarking activity and calculation based on data analytics. Now, before we start with the benchmarking discussion, please note that for any process plant, these are typical objectives, right? Throughput maximization, produce as much as possible, yield maximization, energy minimization, quality giveaway reduction or quality control, and environmental compliance. There are no other objectives outside of these typical goals. That is point number one. The point number two, from an optimization perspective, at a given point in time there is only one objective. Let's say the economic optimization objective today is yield maximization. That means that alone is the objective, and the throughput, energy, quality, environment are all constraints. Remember, we saw an equation y is equal to function of xyz. So here the y will be yield, right? Tomorrow, due to business realities, it could be energy minimization. Then that will be the objective, and xyz will be throughput, yield, quality, and environment, right? So two things. These are the typical 5 objectives, and at a given time there could be only one objective and all others are constraints. Now let's quickly talk about qualitative performance benchmarking, and then we'll go to the main part of quantitative. A lot of times we talk to the plant people, try to understand the plant, get all the data possible. But what we have realized over a period of time is it is actually good to do a qualitative performance benchmarking first. There are various ways and various agencies doing performance benchmarking, and some of them give tiers of performance: first tier performance, second tier, third tier, fourth tier. So we have also developed a benchmarking tier system which is purely qualitative, and what we have found is we have defined 3 parameters, whether the economic objective is known or not. Second parameter, whether systems to do optimization are available or not. And thirdly, what is the actual practice of optimization, where the operations are driven to be economically optimized, or there is no focus on that. Okay, so tier 1 performers are typically those who know what is their economic objective for optimization of plant operation. Like there is yield, let's say, and this doesn't change every day. So let's say there is a particular plant, and yield is very important from economic perspective. Everyone knows that, right? So that is first part, which appears to be very easy part, but if you go to any plant and talk to operating people, their typical first response is, well, we are told what throughput to operate: 100%, 110%, 90%, and we know the various ranges of quality and parameters. So we have to safely operate the plant within the range of quality and parameters and maintain the throughput as is expected of us. That is their typical response. And very few places they know that although I have to run the plant safely and within certain parameters, my plant is contributing to yield, or my plant impacts the environment, and then what is my prime objective from economic perspective. So some people know that. Then coming to the system, it doesn't matter what system is available, but whether those system and work process to work out the optimal parameters, whether they are available or not. So tier 1 performers will have some system with them which helps them to work out the optimal parameters of plant operation and convey it to the operator. And lastly, they do have the practice to periodically optimize their plant operations to ensure their economic objective, by controlling either of these 5: yield, quality, energy, environment, etc., so that their impact on the total site or total company is in the right economic direction. So that is tier 1 performance, right? So these are the people who are determined to have profitable plant operation. They know how to do it and they are doing it. The tier 2 performers are those who know what is the economic objective of operation. They do have systems and work processes, but for some reason their work practice is not to regularly operate the plant on optimal parameters, whatever be the pressure, whatever be the reason. The third tier performers are those who do know what is their objective for optimization, but they don't have any systems to work out optimal parameters, and obviously there is no practice to do that. And the fourth tier performers are those, for whatever reason, there is no focus on optimization, economic optimization, that is, and it is not felt to be important that various people, including the plant operating people, know what is the economic objective of plant operation. So naturally they don't have any systems also in place and no work process in place. So without having any data, if we know these simple things, it is possible to know what is the tier of performance a particular plant is in, right? But this training is one step further. We have to quantify. So we have already talked about all these parameters or the objectives. Now, how data analytics can help to achieve these objectives? So throughput is impacted by unplanned downtime, which could be due to accidents, breakdowns, or process upsets, catalyst limitations, so on and so forth. So all these can be avoided if we detect abnormalities in the plant early. Very doable using data analytics. So and data analytics can impact throughput, increase throughput by avoiding unplanned shutdowns or slowdowns. Yield, energy, quality, environment, all these are basically process objectives and which can be optimized using parameter optimization, the operating parameter optimization. That is also the subject of data analytics and optimization. Now coming back to the performance benchmarking, which is a quick method. So in the non-process example, we said there is some process but we don't really know, but in process plant we know that now this is a simple heater where some oil is getting heated by firing fuel gas, some fuel, and there is some temperature, the coil outlet temperature is being controlled. So we are looking at this diagram to classify the process variables. So controlled CV is controlled variable, DV is disturbance variable, and MV is manipulated variable, a variable which can be manipulated by the operator. So in this case, the operator manipulates the fuel gas to increase or decrease the temperature that he is controlling, which is the coil outlet temperature. And of course, the process is disturbed if the feed oil has a different temperature or a different composition or a different density. That is all disturbing the process, right? Now we have defined these parameters for a reason. We will see that reason ahead. So at this point in time in our workshop, we actually ask people to do a mental experiment. Take any plant that you know well and try to classify the important parameters into CV, MV, DV, right? This has to do with optimization. Now we have seen what an objective is in a typical optimization problem. So this is the one overriding goal for plant, and in this case performance is economic performance. So from economic perspective, what is the objective? It could be throughput, yield, quality, etc. Now the controlled variables are dependent variables, right? These are the y's in equation, if you want to use the simple model analogy. One of these CV can be objective and all other CVs are constrained to achieve the objective, right? From an optimization perspective. The manipulated variables are independent variables. The operator can change these variables in normal operating practice, and these manipulated variables, they affect almost all CVs or some CVs, and of course some of the MVs could be constraints to achieve the objective as well. And the the disturbance variables, the DVs, are again independent variables, but they are not operator changeable in normal operating practice, but they do affect the CVs and the objectives, right? Now we will take example of a reactor. Just think of a reactor, maybe a CSTR, simple reactor. The objective of that reactor, let's say, is to maximize yield, and the process parameters are temperature, pressure, level, right? Now if you have to know what is the performance benchmark, that is what is the highest yield this reactor can, we are basically plotting the same thing. We are plotting the yield, we are plotting temperature, pressure, and level of the reactor. And what we find here is the limiting constraint is the temperature, and the maximum we can increase or decrease the temperature depending on how the yield varies. Let's say increase in this case. So maximum we can increase the temperature is by 1/3 of its range, let's say 1%. By some value, the temperature can be increased by say 10 degrees Celsius, which corresponds to 1% increase in the yield. How we do that? We just plot. In this case, we already plotted temperature versus yield. So we know if the temperature goes up by 10%, the yield increases by 1%, which is basically the slope of the XY plot, right? This is basically the process calculation using data analytics. We are plotting yield versus temperature, yield versus pressure, yield versus level. So we know the impact. The only new thing which we are doing here is finding the limiting constraint, and the limiting constraint is found by the thumb rule of 1/3 of a range. So if we just increase level, increase pressure, increase temperature by 1/3 of the range from average, then what is the impact on yield? That is what we are calculating, and we find out that the yield due to increase in temperature is 1%, which is the lowest, and therefore it is the limiting constraint. So the benchmark performance yield of this reactor is more than 1% of the average yield in today's data, right? If the average yield today is 80%, the benchmark performance yield is about average 81%, right? Uh, Perhaps some of you would not be clear in this, so let me rephrase again. We are looking at this process in terms of parameters, right? Our objective is yield. The objective is impacted by these three parameters. Uh, the new thing which we are seeing is how much of this parameter can be changed in terms of the profitable direction. Now here the yield increases if temperature increases, pressure increases, level increases. Now the question is, on an average basis there is a temperature, how much temperature we can increase on an average basis, right? And that is the concept which is coming out from that statistical paper, that the process has capability to increase the temperature by 1/3 of a range. So if the temperature is 100 plus minus 30 degrees Celsius, the temperature can be increased, right? We are not doing any process simulation. That's the beauty of that statistical approach. You should read that paper to know the statistical basis. So the process has capability to increase the temperature by 1/3 of the range. So 100 plus minus 30 degrees is the range. 1/3 of the range in the direction of profit is 10 degrees. So 100 plus 10 degree. So temperature could be on an average 110 degrees instead of 100 degrees. And if you have that high temperature on an average basis, the yield will go up by 1%. How we know that? You simply plot the yield against temperature. This chart also shows that, but you can separately also plot yield versus temperature XY plot and get this relationship. Okay. So there are two things you are working out. You are working out on an average basis how much a process parameter can be increased or decreased in the direction of profit, which is 1/3, not 1/3 of the range, I'm sorry, 1/3 of the range in the direction above the average, which is 3 standard deviation. So 1 standard deviation, roughly 1/3 of that space, that is the increase which can be done in any constraint. Process has that capability in the direction of profitability. And once you do that, it is easy to correlate the increase in the constraint to the objective by a simple XY plot. Again, no simulation. This works. I have personally done more than 50 plants performance benchmarking, right? Plants, I'm not saying equipment, plants, fertilizer, refining, petrochemical, steel, paper, everywhere. This works. I can personally vouch, and there are many professionals like me who have deployed these standard techniques. We have given commercial guarantees in projects based on the process improvements worked out using this approach. So this is a very powerful approach. Obviously, although it appears very simple, the technical common sense or process concepts are very important when you are doing such calculations and presenting it to the people who know their process very well, the senior people in the customer side. But this is the basic approach. We have taken very simple examples so that concepts are known to you. I know you have very complex processes, but the process knowledge is with you. But this is the approach which we can definitely share with you, and you can utilize your process knowledge and this approach to do performance benchmarking yourself. Okay, so this is an expanded diagram to explain the same thing. There is a process, there is a reactor, it operates at an average value of yield, which is shown by this average vertical line. And to get this average yield, there are average values of level, pressure and temperature as shown here. Now let's say the process is optimized. How it is optimized? It's separate. just let us just say that the process is optimized so that the average yield goes up by a certain level, which is shown by this arrow, which is in a circle. Now, obviously, if the yield has gone up, the level, pressure, temperature would have gone up by some amount, and all we are trying to do is to find out what is that increase in that parameter, limiting parameter needed to get that increase in the yield, right? So we are actually working out the other way. We are working out what is the increase possible in all these three parameters, and what is the minimum increase beyond which the yield cannot be increased further. So temperature is the one which will hit its limits first, and therefore that is the corresponding increase in yield is the yield increase possible due to optimization. Okay, so if you have not seen this explanation in the earlier topic of maintenance process optimization, here is a quick explanation once again. So when we talked about this reactor increase, yield increase example, the basis of the whole calculation appeared to be how much temperature can be increased in the profitable direction, or what is the basis. So the basis is explained in a paper, hydrocarbon processing paper. A reference of that paper is given at the bottom of this slide. This paper was basically written to work this out from a point of view of change in parameter values due to better control or advanced process control. But the logic remains same, that if a process is optimized, the average value of the parameters will change, and what is the magnitude by which the parameters can change. So any parameter will have a certain average and a certain standard deviation. Let's say in this example, if you are plotting the temperature, it will have an average value, and the data will vary around the average, which can be quantified by the parameter of standard deviation. Now, the paper explains many situations and suggests different correlations to quantify this change in average of the parameter. But this correlation, which says the move possible in average value of the parameter in profitable direction, that is above or below the average, is 1.65 into standard deviation divided by 2. Uh, uh, the explanation of how this formula comes and all that is in the paper. It is beyond the scope of discussion of this introductory course. So I encourage you to go and understand it yourself, although a bit heavy statistically. And this is about 0.8 standard deviations, or roughly 1 standard deviation. That means if the process is optimized, then the parameters will move in the profitable direction by the average value of these parameters will move in the profitable direction, and the change in average value will be equivalent to about 1 standard deviation, right? That is the explanation of change in value of parameters. Now, having known how much the average value of a parameter can change in optimized scenario, we just have to correlate the change in average of the limiting constraint with the change in the objective function, which is nothing but an xy plot between objective function and the limiting constraint, and you can very easily find out if the limiting constraint which is plotted on the x-axis, if it changes by a particular value, what will be the corresponding change in the objective function, which is the first elementary data analytic technique we talked about, sorting or XY charting. So hope this whole concept is very clear, very useful, very powerful concept and procedure. You are not constrained by any thermodynamic, kinetic, transfer process data, mass balance, anything. This directly gives you the money increase possible. We talked about continuous improvement. So once we have defined the various type of variables, uh, how we can do continuous improvement in performance, which is not the operating performance. This is like the standard operating process improvement. Here, for CVs, we can question and change the CV limits. CVs are, let's say, this is the product property, it cannot go beyond a certain limit. But who has set that limit? Is that limit too conservative? Can we realize that limit and make more profit? It's a simple discussion worth doing and changing these limits. If some MV is limiting, that means some equipment capacity is a constraint. Maybe it's a simple wall, but that's a capacity which is which is related to some equipment. So that equipment design or replacement of that equipment can definitely be thought of, because we know what is the impact of this change of equipment in terms of money, and that equipment replacement cost versus the benefit can definitely be worked out, and a business case can be very quantitatively made. Finally, there are instances when people change the whole plant itself to some new technology. That time you have a very good advantage that you have been operating the plant for so many years, and you know what is the economic objective and what is the average economic objective we can definitely achieve with the plant. You have been doing it for years together, and what is that being promised by the vendor of the new plant, the licensor of the new plant, that can be very well compared, because capital expenditure in a plant is one aspect, but what is the operating profit of that plant is a more important aspect in terms of money. So you can utilize your knowledge of data analytics, economic objective of the plant to definitely know what is the limit you have achieved with the old technology and how it compares with the promise of the new technology, right? So these are the continuous improvement aspects which can definitely be done using data analytics techniques without any rigorous process models, useful for continuous process improvement, plant improvement, as well as the whole plant comparison with new technology. Right. So at this point in time in the workshop, we usually do the exercise where we say just pick up a plant, your current plant or whichever plant you are comfortable with, right? You generally think about the objective constraints and what is the observation over a period of time with respect to economic performance and these objectives. Identify the variables. Then mentally, how will you identify the limiting constraint? Which constraints you will take out of hundreds of parameters? How will you plot? How will the plot look like? Will this particular parameter impact the objective in a positive way or a negative way? You know, that kind of thing. Mentally, no data. And then perhaps using some data, you can find out a limiting constraint, and then what is the room in that limiting constraint and how it is related to the objective and how much objective can be impacted on an average basis, right? And also some small improvement thinking can be done. So basically this exercise is in two parts. In the workshop, you do mentally everything mentally. Remember how is the data, how much is the range, whether the positive relationship is there, negative relationship is there, and then you realize that it's simple exercise, you can do it mentally, and then all that remains to be done is take the data and do it physically, right? Very much doable. Do it mentally first and then with data. Okay, now that brings us to the last sections, which is plant operations optimization. This is really introduction to complex models, because whatever can be done in terms of optimization and simple models we already talked about. So let's go through this. So again, we can have more detailed discussion on optimization strategy, and we have a couple of examples which we'll talk about. By now, perhaps I don't have to articulate it, but for the sake of completeness and bringing your thoughts out in open, what is optimization? So first of all, you have to have an objective. At a given time, there can be only one objective, all others are constraints. Then working out the optimal setting combination of various parameters, reflux, reboil rate, reaction temperature, pressure levels, etc., so that your objective, if it is yield, that yield is maximum, and while maintaining all other planned parameters within a range, right, including quality. Now this can be done manually or automatically. Manually it can be done using whatever model you have, simple model, complex model, steady state model, whatever model. And this can also be done automatically, and for particularly continuous plants. There is a technology called real-time optimization, which does this online optimization. By online, please do not think every minute it is doing optimization. There has to be a need to do optimization. There has to be change in, say, feed quality or something, and typically that is the frequencies anytime, let's say 4 hours to a week, depends upon how many times the optimization needs to be done. So although it is called real-time optimization, the physical implication is the system is on all the time. It detects whether optimization needs to be done or not, and if it is required to be done, it does the optimization and directly gives set point to the control system or the advanced control system. That's the real-time optimization. Okay. Optimization strategy we have talked about at a concept level. There has to be objective, there is a constraint, and we have to work out the best parameter combination within the constraints. So the strategy obviously consists of stating the objective, what parameters can be changed for optimization, what is the permissible range of operation for all planned parameters, as far as the optimization problem is concerned, what accuracy of the model is required in terms of predicting each parameter, what should be the minimum accuracy that has to be worked out. We have discussed how to do that, and then of course using the performance benchmarking without building a model of the whole plant, we can estimate what is the performance benchmark, or what is the yield, or what is the objective which can be achieved consistently if the plant is operated at a much more optimal in a much more optimal state. And then we know how much data is needed, what kind of data is needed, and more importantly, what data is available with you in your company. Using that, you can take a call whether the data is good enough to build a good model for optimization. So and these details are actually part of that optimization strategy, which you can do yourself. And objectives, which we already talked about. We also talked about that at a given point in time there is only one objective. Now this is an example of a complex model and optimizer for a crude distillation unit in a petroleum refinery. So the model was built using 2 years of plant and lab data, and there were about 100 plant parameters, measured parameters, which is temperature, pressure level, etc., flow. And what was the output of this model? The output of the model were 3-4 type. One, of course, is the optimal yield achievable. You know, if you're having a 45% yield right now, you could perhaps have a 47% yield. And how? So all the optimal parameters which can be changed by the operator were worked out. I think there were about 15 such parameters, and for optimization. So what is the optimal yield achievable? What is the optimal setting of parameters for achieving that optimal yield? Then all important stream properties which are otherwise done in lab, they are calculated uh, for the current operation as well as for operating optimized operation. And also, what are the abnormal parameters? You know, what is the model expected value based on a very accurate model, and what is the current value? All these are worked out, right? Uh, so this is how one complex model, accurate model, can be built, and this is case study of a plant. Okay, of course, this project is not over, and but we have built a model that is a milestone which is definitely achieved. And the interesting part is the objective. We asked the same question: what is the objective of economic optimization? And there were different answers by different people. But when we really explained the concept, what we are trying to do, and we had a discussion, small discussion with the experienced technical services team who were very enthusiastic about this project. The project objective came out, economic objective came out as distillate yield, you know, maximization of the distillate yield. Uh, so, so there is no better way than discussing with the experienced people at the plant and technical services. And the quality limits of various stream properties were taken, but only control limits were taken. See, in lab they do hundreds of parameters, but they do it at different frequency. There are only few 10, 15 parameters which are done very rigorously, perhaps every shift, because they are the real control points. All other properties are important, but they are not really used for you know, as a hard limit on the plant performance. So that has to be kept into mind, because otherwise a lot of customers insist on, you know, I want this quality in the model. But then if you look at data, there were only 2 lab samples done in the whole 2 years. So if it is such an important parameter, why only 2 times, or you know, at the frequency of 1 time in a year? It simply means it's a not an important parameter at all. And secondly, if you want to build a model using data analytic techniques, if there is no data, it is impossible to build a model. Anyway, that was one point. And then we found that we didn't really get good models with small amount of data, 3-4 months data. We had to take full 2 years data to really get an accurate model. It is important to say here that at the cost of repetition, no crude assay data was requested, no thermodynamic data, no kinetic data was requested from client, and the basic model building work took about a couple of months, right? And finally the model was built, the optimizer was run with all these 2 years of data, historical data, excuse me, and it was found that if they have been using optimizers in those last 2 years, they could have increased the distillate yield by 0.35% on average, which means that the net profit could have gone up by 15 crore rupees, or about $2 million per year, just by optimizing this one plant performance, CDU. At this point in time, it's a good time to let you know what service we can provide apart from the consulting services discussed in the first session. we can give an alert service. Basically, the plant engineer sends all those 100 parameters to us by email. Our engineer works out the optimal parameters, abnormal parameters, and all that stuff and sends it back, right? So the plant engineer knows I can increase my plant yield by 2% if I change my plant parameters to this new combination of optimal plant parameters. I will change it. I know all the product properties which are there, and when the plant is optimized, what will be the product properties. And at the same time, I know these are the two parameters which are felt to be abnormal compared with the model values. But I know one measurement is wrong. Therefore, I don't have to do anything. The other abnormal could be real abnormal. Let me do some investigation, right? So this is a remote service which we can provide. It's called Benchmark Alerts. So without buying any software, and these fees are per use basis. You know, if you use our service once, you are billed for 1 day usage, right? And that's what we already talked about this, and all this analysis is done by a model which is built earlier using the data and proved to be accurate, right? And these rates could be reviewed. This is a bit older slide, but the concept remains same, that there is no long-term contract. You don't have to buy any software. It's just pay per use service. Let's say you use service 10 times in a year, right? Only when you think you need to optimize perhaps, then you will only pay for 10 times usage, and per usage price is 30,000 Indian rupees plus taxes, which is roughly 350 US dollars per usage, and plus taxes if any, right? So this is absolutely pay per use benchmark alert service. Now there is an interesting paper that we have published. The link, this is actually a PDF file on LinkedIn, and the link to that paper is on our website www.benchmark1.in. It's a petroleum refinery benchmarking paper. Just couple of slides, which is a very interesting application of simple data analytics to the complex subject of refinery economics. So this refinery is a larger refinery, about 300,000 barrels per day refinery, 15 million metric tons per annum refinery, and has about 30 plants. And in this paper, what is explained is a data which is available on the company website, the annual reports, etc., is taken, and the objective of refinery operation. You know, there is a plant, but there are 30 such plants. There could be crude unit, FCC, hydrocracker, and all those stuff. But there is a whole refinery, and there is an objective for the whole refinery also, and that objective is known, which is maximizing the GRM, the gross refining margin. That is a very established term in petroleum refining, and refineries do maintain and monitor and maximize the GRMs. So using our same simple data analytic techniques and conceptual analysis, it was found that the GRM can be predicted very accurately. The R square was 92% or 0.92. You know, the 92% variation in GRM could be explained using this simple equation, which is at the bottom of the slide, which is a function of 4 parameters: refinery throughput, a very visible parameter; distillate yield, again a very visible parameter; and then the parameter which we took from their annual report, which is ratio of sales revenue versus annual crude cost. This is basically the market incentive, right? Irrespective of how well you operate your refinery, the price that you get for your products and the crude that you buy is the market incentive. That is what we have tried to quantify here. And of course, it is thought that crude price has a lot of impact on the GRM, so we took that parameter also. And this equation can be analyzed that the highest impact is the market incentive. Uh, but at the same time, the refinery, or particular the operating people, they have very little or no control on this market incentive, and the refinery throughput and distillate yield are the main parameters, and the crude price didn't have a lot of impact, right? Out of this refinery, the refinery throughput is watched, maintained, and worked upon by literally thousands or at least hundreds of people to make sure that the refinery is operating at a particular throughput. And typically, the refinery, if it is operating, will be operating in the normal or near normal range of throughput. So what really impacts the GRM is the distillate yield, right? It definitely impacts more than the throughput in the normal throughput range. So this is what we could find, and uh, using this very accurate model, if you will, we calculated that what will be the impact if the yield of the refinery is increased, distillate yield of the refinery could be increased. So on the first column, if you see, these are a possibility of improvement of the yield. Let's say 1% yield is improved. Then it says what is the calculated possible GRM increase. This is 80 cents per barrel. In refining, they talk about GRM in cents per barrel, which is huge. Typical GRMs are around $10 a barrel. So this is $0.8 a barrel. And if you extrapolate it to year, it comes to $80 million a year, or about 660 crore rupees, or about 20% of their net profit, right? So 1% yield increase comes under achievable category, right? It's not totally impossible. So that's the order of magnitude. It can be envisaged by optimizing the operations of the whole refinery, not a particular plant. Uh, but then that's the incentive, it is available. So one thing it does demonstrate the power and utility of the optimization at a more modest level. It also shows how such a complex subject can be made very easy and quantified using very simple data analytic techniques and simple data. This is like 5-10 years of annual report data, right? Nothing more than that. So we hope this gives you a good overview of the complex models, introduction to complex models, as well as to applying these simple techniques to large and complex systems like a refinery performance. And the paper also said if you have any question, please contact us. So you can contact me. My name is Samir Gizre and my email ID is samir.gizre@benchmark1.in. I am located in Pune, India. Then we have a section on market available systems for plant operations optimization. Most probably you know these being in industry, particularly continuous process industry. So this section is there to differentiate between these various systems and know what is the primary goal of these systems. So the systems are like optimizer or real-time optimizer. This is, we are talking about a plant, right? We are not talking about supply chain optimization and things like that. We are talking about plant operations optimization. So the highest level of optimization can be achieved by real-time optimization or any optimizer, then which is accurate and rigorous enough. And the second level of optimization, there are systems available for dynamic plant-wide optimization. There is well-known APC, Advanced Process Control, which is very well known in refining, petrochemical, and large chemical plants. Of course, there is DCS, which is more of a control system these days because all the control logic, etc., are broken and taken over by APC. So DCS remains at the single loop control level. No optimization is done there. And of course, there are production planning models which are also doing some optimization, but the goal is different. So we are comparing these systems. Uh, so if you, as we discussed, the real-time optimization or optimization is the highest level of optimization. It is quite rigorous, very accurate, and almost all important parameters have to be in the model. And this is global optimal. You can send direct set point to APC. There is no trial and error. This is very deterministic statement that this is the maximum profit I can get, and these are the parameters which are required. Just set these parameters in the plant in a closed loop manner. Then there is a dynamic optimization technology available. Before that, which is basically a fusion of various APCs in the plant. The level of optimization is of course lesser than RTO because this is basically doing trial and error optimization within the limit of parameters given by optimizer or by the operator. And of course it does send the set point to APC, in that sense it is online and closed loop system. But the models are not rigorous and the accuracy is only directional accuracy like APC, and not all parameters are included in the model. Only the APC parameters which are measured parameters, inferential properties, only those are included in the model. The APC discussion is same. Only thing, APCs are usually for a few section of the plant or a plant completely. So this is APCs are then fused together to form the dynamic optimizer. The DCS doesn't really do any optimization. It is basically for single loop control, single parameter control, and it is opening and closing the valves. Okay, it is definitely meant for control only. Then coming back to the LP models, again people say we have another LP model, it is doing also optimization. Why do we need plant optimization? So again the difference is in the rigor. It is not a very rigorous model. It is not a rigorous model at all, and it is directionally accurate, and not all parameters are included in the production planning. The main goal is optimization with respect to maximization of the GRM by maximizing the product value, minimizing the feed cost, and the major constraints of capacity and quality are included in the model. And the goal is primarily meant for planning of production volumes and let's say crude purchase or feed purchase in terms of economic decisions, right? This is definitely not meant for plant operations optimization. Nobody is using planning model for doing the actual plant operation optimization. You cannot just work out optimal parameters from this model and feed it to APC in the plant, right? So that we hope that gives some difference between APC and all these systems what we have talked about. It is also interesting to know what kind of a model at a conceptual level is there in these systems. This is not really an essential topic, but some people could be curious. So in any of such optimization system, it is a decision making system. So it will have two parts. One is the system model and one is the decision making part or the optimizer part. Okay, so this basically talks about the model, system model in each of these systems. Right. So in the optimizer, traditionally there is a rigorous first principle material heat balance model, and obviously the model has to match plant. So either the model has to be very accurate or there have to be some data reconciliation to be done. So depending upon the particular technology, there are various subsections in this optimizer algorithm, and the rigorousness or data reconciliation is required, accuracy is required, because the system directly gives set point to the APC. Now the rigorous models are also available as simulation models, right? Everybody has simulation models, but one just cannot calculate set point and give it to APC or control system. That is the difference between steady state optimization and optimizer, a steady state model and optimizer. Now, obviously, new concept of hybrid model is coming where people are trying to fuse the approach of steady state, rigorous models, and database models. But it's clearly an emerging technology right now. Now, if you talk of APC, what kind of model it has? So, to understand the model structure in APC, imagine any pair of CV and MV in your plant. Let's say the reflux flow and the column top temperature, or the reboiler flow and some column bottom temperature, or something like that. Okay. Now you add the dimension of time. Okay, so if you look at a DCS chart and let's say that reflux flow has changed suddenly, which is called as a step change in process control language, you typically observe a first order kind of a response in the control variable, in this case the column top temperature, right? Now this exactly is called as a sub model in APC, and the plant model in APC is simply a collection of all these sub models, right? So all the controlled variables in the plant versus all the manipulated and disturbance variables in the plant. That's the system model which is in APC. Now it is easy to understand what is the model in a dynamic plant-wide optimizer. So then you again fuse these individual APC models into a large model. Of course, it will have logical internal connections, but you don't really have to make new models. You just take these APC models and fuse them together using software tools which are purpose made for this. And then production planning models again are linear models, and basically it is a large parameter optimization, and the base for such models is the yield vectors, which are generated from historical plant and lab data, and which is basically, yield of products correlated with plant and lab parameters, right? So that's the model in the LP model. There is no heat mass balance models, etc. in the production planning LP models, right? Now, if you come to DCS, DCS doesn't really have a process model. The only process model it is there is in a PID loop, which is basically a dynamic model between the set point and the process value, which is again a first order model which is tuned for every individual loop or a cascade loop. Otherwise, there is no process model per se or any optimization per se in DCS control system these days. Okay. Of course, the DCS can give very good visibility of the entire plant situation to the operator or engineer who can work out the optimal plant parameters using any system that they choose to use. Okay. Now we have talked about this optimizer and optimization strategy, so we will not repeat this again. And with this, we come to the end of the session. Uh, it's quite an interesting session in our workshop where we get direct feedback after a long day of various new things, some very interesting and some few boring ones, depending upon the person. And it's very interesting to get the feedback, but this being online recorded training, we will miss that part, but I can always request you to please capture your feedback right now on a piece of paper. What was your learning? What do you really think you have got a new thinking method? Maybe there are some unanswered question. Maybe you have some feedback for me or the training as a whole. What path forward you think as a professional? How do you want to use these techniques in your immediate work? All these are pointers which I request you to please think over, and we will be very thankful to get your valuable feedback by email. You can please send your feedback by email to info@benchmark1.in. So it will be very helpful if you can talk about all this feedback and your contact details and reference of the training. Okay. We also request you to visit our website, which is benchmark1.in. This one is number 1, and hopefully you will find some interesting stuff there as well. And if you want to discuss anything further, you can please send an email to me. My name is Samir Gizre, and my email ID is samir.gizre@benchmark1.in. And in your email, we request you to please give a brief objective. What do you want to discuss? Please mention a number to call you and a suitable time, your local suitable time where you expect the call, and we will try to call you at the time of your preference. Right? So I really thank you and wish you a great day ahead or a great evening ahead, depending upon where you're located and what you're doing. So thank you once again, and we will look forward to your feedback. And in any case, we hope you will enjoy this new approach of thinking, and your life and work will be much more interesting applying these techniques in your day-to-day life and work. Thank you.